Understood.
That's the camera. Now, when you select it, it automatically goes live. So go ahead and switch it back to the screenshot. This one right here. So this is,
How fast is the
oh wait, go ahead and select that.
stream?
Yeah. This part right there. Go ahead and click OK, because I didn't make any changes. But, we have good bandwidth on it right now. Oh, the other thing is, you see how it's changed now. You'll see
Yeah.
the camera move. So we do have a little bit of a delay. There's actually audio as well when you have the camera or the desktop presenter selected. When you go to intermission, coffee break, or the other slide, it will not have audio. To this one, because that's the one that's
Before we start, I just wanted to make a quick announcement. Down on this table, we have nomination forms for the DMP Executive Committee. If you have not done so already, we are nominating Rolf Ent for member at large. So please come down and fill out one of the forms during one of the breaks and just put it in this box after you've signed both the form and the envelope. So with that, our first speaker today is Brad Philippone, and he's going to tell us about a search for the neutron electric dipole moment.
Wow, that works. Thanks. Thanks very much. I'm happy to be back. Thanks to John and the other organizers for inviting me. So I'm going to tell you a little bit about the neutron electric dipole moment in general and about the experiment in the U.S. That we're pursuing. There was a talk last year by Doug who talked about some aspects of it. I'll try to go into the more recent. Actually, a lot has happened in the last year, and I'll update you on the status and progress with the experiment since then. And since I'm talking about an experiment that doesn't exist, I won't have any data to show, but I trust the next talk will have some new results, so hopefully you can wait for that. So I'm going to tell you about first the science of electric dipole moments, try to make some connections since I'm here at JLab with the physics here. I'll talk about the status of neutron EDM searches, the previous work, and then spend some time talking about the experiment that we are developing. The technical challenges, it's quite a challenging experiment, as you'll see. We'll talk about the recent progress and also the path for construction and data taking. And then I'll finish up with discussing worldwide efforts for neutron EDM. It'll turn out we're not the only ones doing neutron EDM. So an EDM, electric dipole moment, I'm teaching Phys 1 at Caltech. We just finished last week. Dipoles, just a positive and negative charge separated by some distance. Dipole moment is the product of the charge times the distance. So if you assume the charges are separated by something a tenth of the nucleon size, or a tenth of the nucleon size, you get an electric dipole moment about 10 to the minus 14 centimeters. However, if you go and try to measure it, you discover it's actually about 12 orders of magnitude smaller. So there's something obviously preventing it from being a natural size, and we know it's a CP violation, or CP symmetry. So what is the connection with electron scattering? In fact, the EDM shows up in the electromagnetic current. It's out here at the end, F3, P and T odd form factor. This is the standard form factors you crush here at JLab. Also the the parity violating axial form factors here. So F3 is related to the neutron EDM. The Q squared equals 0 limit of this form factor is the EDM. But that's not the only place it shows up. It also shows up somewhere else. It's also related to transversity. I trust most people. I put a definition for the two people who don't know what transversity is. Probably 0, actually, in the audience. And so the transversity structure functions are here. If you take the difference between particle and antiparticle transversity, sum over all x, you get the tensor charge in the nucleon, and the electric dipole moment of the neutron is related to the tensor charge via the quark EDM. If the quarks have an EDM, it sums up like this. So in principle, you can access this structure function, this form factor here. There is that little factor of 12 orders of magnitude, but this is JLab. I'm sure by the end of the talk, somebody will figure out an experiment with a little asymmetry or something to attack it here. So the thing that keeps it so small is that it must violate time reversal symmetry and CP. The easy way to see that is if you have a neutron with an electric dipole moment, it's a vector, so it has to point either along or against the spin. This one is along the spin. If you reverse time, J flips, but the charges don't move, and so you get this particle. So if this is the neutron, this is a distinguishable neutron because it has a different EDM compared to the spin. And so that would be 4 states. We know there's not a distinguishable neutron. And so the existence of an EDM would violate time reversal symmetry. The motivation for the real motivation for searching for EDMs is the fact that this CP symmetry violation could be a window to new physics beyond the standard model. And that's one of the main motivations. Even with, as I'll try to demonstrate with a few slides, beyond the data from the LHC. The other reason why it's interesting is because it's suppressed strongly in the standard model, so that if you can, you still have a big window between the present limit and where the standard model limit is. So there's a lot of lever arm for new physics. There's also the issue of the matter-antimatter asymmetry and the Sakharov criteria, which could explain this using particle physics, but it requires a large a new source of large CP violation. And so, where do the elementary electric dipole moments come from in hadrons or leptons? In the standard model, there is a CP violation. We all know in the CKM matrix, there is a built-in CP violation. But with that, you still electron and quark EDMs are 0 in first and second order. You actually need 3 loops to get a hadronic EDM. You need 4 loops to get an electron EDM. And so all these higher orders suppress EDMs in the standard model. There's an example of a quark, a loop that could give a quark EDM. The standard model prediction is about that, 10 to the minus 32 e centimeters with an error of 1 in the exponent. It's so small, so it's hard to calculate. And if you convert that to Fermis, that's really e Fermis. That's a pretty small number. As I remind you, this is the 6 orders of magnitude lever arm you have to look for new physics between the present limit and the standard model. Is there a, so if we're going to go look for it, is there a reason to look for it? Is there a chance that we're going to find something? Is there a natural source for CP violation? In fact, there is. In fact, the model that was exciting particle physics, particle physicists for so long, and one of the motivations for the LHC, looking for supersymmetry, allows for lots of CP violation. There are a number of phases that could exist. CP violating phases, and you have to guess their size. Like, oh, I'm too close. That's why. Sorry. If they're of order 1, you can calculate an EDM. That's about 10 to the minus 24 e centimeters if the SUSY scale is 1 TeV. But no, that's already bigger than the present limit. So already we've suppressed. There's what's called the strong SUSY CP problem. There's already some sort of problem. This phase has to be of order 0.01 to be consistent with the present data. So looking at how EDMs exist with and after LHC, as I said, it must be new physics because of that big lever arm. Also, the scale, the mass scale that you're sensitive to can be quite large. This is a recent calculation from McKean, Poskilov, and Ritz, where they have very heavy fermions, but TeV scale gauginos. And they show versus tan beta and the scale, lambda scale TeV, 200 TeV, that's not a misprint, that's 200 TeV, 400 TeV. This is the present limits on from electric dipole moments, and this is what's permitted with a Higgs mass of 126. If you were to improve the electric dipole moment, the scale that we're talking about is about 2 orders of magnitude. We're looking to improve the EDM by 2 orders of magnitude, 10 to the minus 28 e centimeters. And that pushes it off to the graph closer to 2,000 TeV. So there's quite a large scale for new physics accessible with EDMs. So the EDMs, I'm going to focus on the neutron. So it's the hadronic EDMs. Hadronic EDMs come from a variety of sources, from the quarks and gluons, and also from this parameter that's supposed to be in QCD, called theta QCD. This is Lagrangian. I'm not going to talk about it, but there are 4 terms. The 3 gluon term is generally considered small, but then there's a electromagnetic quark EDM, and then there's what's called chromo EDM, which is induced by gluonic interactions, and this is observable in heavy atoms. That's the best way. It's also visible in neutron, but it is the dominant term in heavy atoms. And so, if you've looked at all into EDM, there appears to be lots of different places people are looking. It is something of a zoo of particles, and why are we all doing it? The reason is because there's no guarantee that some system will have a positive EDM, and if you find a positive EDM, it doesn't mean another system will have a positive, or if you don't find it, it doesn't mean the other system won't have it. And so to search for it, you've got to keep your options open. You can look at paramagnetic atoms to see electron EDM. There was a recent dramatic improvement in that recently published. Diamagnetic atoms give you sensitivity to this chromo EDM, this gluon-induced quark EDM, and theta QCD, and the neutron gives you sensitivity to both. In fact, I can show you just to see the scale. Here's the neutron sensitivity to theta QCD, the elementary quark EDMs, and the chromo EDMs. And this is for mercury, which is a diamagnetic atom. You see the sensitivity is suppressed, but in fact the limit is about 3 orders of magnitude, but the sensitivity is suppressed by about 100 to 1,000 because of atomic physics effects. And so let's focus now on the neutron. I'm here to talk about the neutron. The first search was actually looking for parity violation by Purcell and Ramsey using neutron scattering. And so they developed this crazy idea of rotating spins of neutrons to look for this parity violation. And after somebody else found parity violation, they said, well, what else can we do? Oh yeah, EDM also violates time reversal, so let's keep looking. And so they continued to search for electric dipole moment. And so that experiment here was improved and improved and improved. People started using slower neutrons here. These were neutron beams. At this point, around 1980, people started trapping neutrons, a process which I don't have much time to speak of. It'd be another whole seminar. But I also work on other experiments using ultra-cold neutrons, or we call them UCN. They're very slow neutrons that can be trapped inside material bottles. Slow being 5 meters a second. A sprinter could outrun them. But if you can collect enough of them, then you can trap them for a long time and make a measurement. And so that you get huge sensitivity by using ultra-cold neutrons. And the present limit, you'll notice, the recent measurements have only made sort of incremental changes. We hope to make a jump of about 2 orders of magnitude with the next round of experiments. And so how do you access it? What are we going to have to do to improve the precision? What is the precision of an electric dipole moment? Generally, you're going to measure an energy. The D dot E, the electric dipole moment, interacts with an electric field. This is the energy. And if I want to understand how well I can measure an energy, I can use the energy uncertainty principle. So the error in the energy will go like h bar over delta t. Remember, the dipole moment goes like E electric field, and so delta, I take delta E over E, and so the error in the dipole moment goes like the energy error divided by the electric field, or the h bar over the counting time. This Tm is the time that you observe the system. It's a coherence time. The longer you can look at the neutron, a single neutron, the error will actually improve linearly. Of course, you can't look forever on a single neutron. You've only got its 10-minute lifetime, and so that's certainly a limit. And then, of course, you can have lots of neutrons, lots of measurements. You can repeat the measurement and get a root n improvement. And so that's sort of how you scale the sensitivity to an electric dipole moment. You need a big electric field, you need long measurement times, and you need lots of neutrons. Somewhat obvious. To make the measurement, you put generally you put a magnetic and electric field in place. You insert a neutron, flip it spin 90 degrees to the field, and the magnetic moment causes it. The neutron's magnetic moment causes it to precess in the field. And so what you want to do is you want to measure this frequency of precession. Obviously, if there's an electric dipole moment, there's a d dot E term in the energy which will shift that frequency. So if I flip the electric field back and forth, the neutron precession frequency changes. And so by measuring that change in frequency, I can extract a electric dipole moment. I obviously have to control the magnetics very well because that changes the frequency as well. And we're talking about, as you can imagine, we're looking for changes in the frequency that are a part in 10 to the 9th, a part in 10 to the 10th, due to the electric dipole moment. The previous experiment the most recent publication from the Institut Langevin in Grenoble, that's where the 3 times 10 to the minus 26 limit comes from. That's a 90% confidence level. That used ultra-cold neutrons. They actually trapped a half of a UCN per cc. They had a bunch of cc's. And so they didn't have that. They don't have not many neutrons, less than the number of neutrinos in this room from the Big Bang in density. They have a big magnetic shield. They have electric fields of order 5 to 10 kilovolts per centimeter. And they measure a single neutron or a bunch of neutrons on the order of 100 seconds. And that's where they get the limit. So we have to compete with that. We have to compare with that. And we will. So we want to improve. In order to improve, as I said, we need more neutrons. We need a bigger electric field. The error bar goes linearly. One way to do that, which is what we're pursuing, we can use a dielectric material that has a strong, high dielectric strength, so to prevent breakdown, and see if we can get higher electric fields. You also need to minimize key systematic effects. This previous experiment rediscovered a systematic effect during their data taking. They discovered that on Tuesday they got a non-zero EDM here, but then on Thursday they got a non-zero EDM of the opposite sign down here. And the following week was somewhere in the middle. And so they spent a year chasing down why their EDM was jumping around. And it turned out to be, these neutrons I said are moving at 3 or 4 meters a second. It was a relativistic effect that caused it. There is the neutron's velocity in the electric field, there's a V cross E, which produces a magnetic field, and that can change the frequency. That's a systematic effect that it was predicted, Gene Cummins predicted it, but everybody said, oh, it's going to be too small, we'll never see it. Turned out they had the sensitivity that it finally showed up, and they had to chase that down. And that was due to non-uniformities in the magnetic field. And so you have to have highly uniform magnetic fields. You can try improving the shielding. Our experiment will take advantage of a superconductor to reject external fields. It's also pretty important to have a way of monitoring the field. It's called a co-magnetometer. Co-magnetometer is the best. That means it sits right and samples the same volume as the neutrons. It doesn't. If your neutrons are here and your magnetometers are here, you're not really sure what the magnetic field is in there. And so we'll try to improve all these things. The technology that's being used worldwide, the new technologies are in red and green. The green ones are some of the ones that we're taking advantage of. Using superfluid helium-4 to produce the ultra-cold neutrons. We can get a big boost in density via that. Using liquid helium to improve the high voltage in the electric fields. Using cryogenic magnetic shielding, including superconductors, and co-magnetometers. We will have helium-3, living polarized helium-3, which a lot of people here have a lot of experience with. We'll inject polarized helium-3 along with the neutrons in order to measure the ambient field using squids to keep an eye on the helium-3. These co-magnetometers, if they actually live with the neutrons, it's the most effective way to do it. So the collaboration I show here, you'll probably recognize a lot of names. There are people that work here as well. There's a community. I guess we all sort of know each other. We've put together this fairly large collaboration to attack this problem. As you'll see, there are a lot of different technologies and challenges that are present that need to be solved. It does require a fairly big group to pull this off. We propose to do the experiment at Oak Ridge at the SNS spallation neutron source, 1 GeV proton beam on a spallation target right here. And we have a building out here along what's called the fundamental neutron physics beamline. Nuclear physics paid for a beamline, one of 22 beamlines that were built by basic energy scientists to do material science and condensed matter. We have one beamline to do nuclear physics, and we will mount the experiment there. The experiment, our experiment, based on a concept by Bob Golub and Steve Lamoureux in '94, involves producing ultra-cold neutrons in superfluid helium. Since you've got the superfluid, might as well use it for a dielectric. Put it between your electric fields, see if you can get higher electric fields. Since you're talking about helium, why don't we put polarized helium-3, inject that in the system as well to monitor the magnetic field. As I'll mention, the helium-3, of course, would have an EDM, but the electron cloud in the helium-3 suppresses the effect on the helium-3. Basically, you put an electric field, the atom distorts so that the nucleus, the positive nucleus doesn't feel any field, otherwise the whole atom would move in an electric field. An atom doesn't move in an electric field, a neutral atom, because the charges redistribute. So there's a suppression. And so it's much smaller than we could observe, so we can use it as a magnetometer to monitor magnetic field variations. And since we've got helium-3 in there, why don't we use that as a monitor of the neutron frequency? We actually let the neutrons capture on polarized helium-3. There's a big spin-dependent cross-section. When the neutron and the helium-3 are anti-parallel, they have a big capture cross-section. When they're parallel, they have a really small capture cross-section. It changes by like a factor of 1,000,000 between whether it's parallel or anti-parallel. And so we can take advantage of that trick to measure the frequency. I'll show you how to do that, how we do it. And we believe we can, with these techniques, achieve a factor of 100 improvement, which is about something like 3 × 10⁻28 after 3 years of running at 90% confidence level. That's what we guesstimate. So what's our technique compared to the previous? I mentioned this business of the helium-3. Previously, in fact, Ramsey and Purcell invented this technique, the Ramsey separated oscillatory field trick. What you do is you come in with a polarized neutron polarized along the field. You rotate its spin 90 degrees, and so now it's perpendicular to the magnetic field, and it starts to precess. So it's precessing around the magnetic field. You let it precess for a fixed amount of time. You know how many times it's going around. So you start here, you go around 1,000 times, and then when you get back here, you put the same pulse on, and so now you've got the spin up. And then you measure how many spin-up neutrons versus spin-down neutrons. If the neutron actually didn't quite make it around because of the EDM, it won't quite go back up, and you'll get not a perfect spin flip. And so measuring that asymmetry as a function of this frequency that you apply in this fixed time, you can measure the EDM. This is an example of just tweaking that frequency and watching the asymmetry change. And so what you do is you go to a very sensitive point here and then flip the electric field and see if you see a shift. In our experiment, since the neutrons and the helium-3 are coexisting, the neutrons can capture. When the neutrons capture, they produce a triton and a proton. We have helium-4. The triton and proton can ionize the helium-4. That produces UV light, which we can down-convert to visible and detect that light. So we can actually measure photon counts as a function of time. This is a simulation of what that would look like. So we're actually measuring this frequency over hundreds of seconds. This count rate is a function of time, and extracting. It's a lot like the G-2 experiment. They have a similar picture where they measure for many cycles, and by doing that many cycles, you get high sensitivity. And so we will take advantage of that technique. Let me show you how that works. I'll put it all together into the experiment. There you sort of see the scale of the experiment. We start with, we have to have polarized helium-3. To produce polarized helium-3 with an atomic beam source, we inject it into the liquid. We then transfer it using phonons. So by temperature gradient, we can push the helium-3 down to here. So the helium-3 is now in the measurement cell. Now we need some neutrons. So we have a period of illumination with cold neutrons. The cold neutrons are about 1,000 meters a second. When they scatter with the phonons in helium-4, they become a few meters a second, and then they're trapped. They're trapped inside our box. And so now we can detect them. So now both the neutrons in helium-3 are aligned with the applied magnetic field. We produce a pi/2 pulse to rotate the spins. And now, since the helium-3 magnetic moment is a little different, it rotates a little faster. And so they get out of phase. And whenever they're anti-parallel, there's a high probability that they capture producing light. So whenever they, you'll see my little light burst there. And so you watch that time dependence of the light is how you measure the frequency. Then after a while, first of all, you run out of neutrons, and then the helium-3 polarization goes down, and so you got to clean the whole thing out again and start over. And you flip the electric field and do the same thing. You do this over many cycles. Cycle time of order, we're hoping to of order 1,000 seconds. And then you flip the electric field and start over. As I mentioned, the Helium-3 EDM is about 5 orders of magnitude smaller than the neutrons because of the suppression, and so it acts as a co-magnetizer. It measures the magnetic field, not the effect of the electric field. We have another trick we can apply. There's an atomic physics trick where you, if you have, you're doing spin rotation, you have a magnetic field, B0, and the spins are rotating along here. If you also apply a AC field, not at the rotation frequency, actually a large, relatively large field, that's AC, you can cause the neutron and the helium-3 to precess in that plane. You can vary the precession frequency. In fact, you can make them the same. You can lock their frequencies. I have a, does this work? Yeah, if I go this way. I have a movie which shows the red is the helium-3, the neutron is blue. Whenever they're in the plane, which is this plane here, you'll notice that the two spins are aligned. When they're out of plane, there's a little bit of, they separate a bit, but whenever they're in plane, they're locked in phase. And so you can suppress the effects of external magnetic fields by keeping the helium-3 and the neutron relative angle fixed. That's another trick that we could use with quite different systematics to independently do. For example, if we see an EDM with one technique, we can use the other technique to confirm it's not some artifact of systematics. And so the scale, how do we win compared to the old experiment? This sort of is a table. I have a bunch of tables which I won't go through in detail. You can go back and look at them at some point and post the talks, I guess. And so we win factors of 5, 7, 2 to get a total factor of about 100. This is our sensitivity per day. So in a day, we can already beat the limit by almost a factor of 10. This is so showing the systems, the components of the experiment. There are a lot of challenging components. There are dilution refrigerators. There's the helium-3 polarizer. There's injection. There's cold neutron beam guide. There's magnetic package, both cryogenic here with magnetic fields, and then an external magnetic shield, which is at room temperature. There's a central liquid helium volume, which includes high voltage, light collection. We have to get visible photons out. There's squids. Of course, we have 1,000 liters of 300 millikelvin superfluid here, which is challenging. We also have, as another component, offline test facility at the research reactor at North Carolina State University to test components of this and some of the concepts. And so, as we often say, there are some technical challenges to the experiment. So I have a list, and we have this now running joke in our collaboration meetings. Now that we think we've checked all oh, that's physically impossible, you can't do that, or that particular thing, you cannot build that, it's impossible. We think we've demonstrated that. So the rest of it is just engineering, putting it all together. However, what we require are things like the whole central volume has to be non-conducting because of RF heating and magnetic Johnson noise. It has to be friendly to polarized helium-3, friendly to neutrons. It has to be friendly to ultra-cold neutrons. If it eats ultra-cold neutrons, we're dead. We have to have helium-4 that's clean. If it has the natural concentration of helium-3, the neutrons will be gone in 10 seconds. So we have to purify the helium-4 to parts per trillion, which is about 1 million times better than natural helium. And we need this big chunk of superfluid helium at 0.3 K, with obviously no leaks. We need high electric fields, 80 kilovolts. We're hoping to get of order 10 times what the previous experiment had with the liquid helium. We can't have electric field breakdowns. Our squids will die. We're working on that to see if they can survive a few sparks. But that's a challenge. We need magnetic field suppression, external magnetic field suppressed at 10 to the minus 5 so we can make the squids work in systematics. We need ppm uniform magnetic fields. And perhaps the hardest part of all, we need all of the above approved for operations in a national laboratory. So another long table, projected systematics. We have a long list of systematics which are all smaller than our statistical precision of about 3 to 5, 10 to the minus 28. The biggest one is this, what's called the geometric phase. This non-uniformity in the magnetic fields produces about 2, 10 to the minus 28 in our optimal configuration. And so we believe we've got it control over all the known unknowns. These are the systematics that will come and bite us. Of course, when you're pressing things a factor of 100, there could be new stuff. That's why you need separate handles on understanding the systematics. And that's a big deal. In fact, one thing we can do with the polarized helium-3, we can change the temperature of the volume by 100 millikelvin. What that does is it changes the helium-3 mean free path. At 450 millikelvin, it's about a millimeter. It's colliding with phonons in the helium-4. If we lower it to 300 millikelvin, it's ballistic. A meter is the mean free path. And so we can change, that totally changes how the helium-3 samples a magnetic field. And so that's a big effect we can use to understand magnetic field systematics. So let me spend the last few minutes talking about the status. This is development sort of since the last year. We had, in 2012, there was a big review of fundamental neutron physics by NSAC. Neutron EDM was voted the highest priority in this subfield. However, they saw there were still some critical technical issues that had to be solved. It hadn't been solved after several years of R&D. We've been working on R&D for quite a while. And so DOE and NSF wanted to know, is there a future to this experiment? So they actually gave us a 2-year drop-dead deadline. They said, you deliver in 2 years, or we're going to stop this. And so they put us to work for 2 years. In fact, one of the things that helped get there was they took us off this. MIE is a major item of equipment in DOE lingo. So we used to be a construction project, and so we had CD0, CD1. Everybody knows what those are here. And we had to go through all of that with technology that we weren't even sure what it was going to look like, and so it's not really the right way to do you can't do a project, you can't operate it, you can't construct a project in the DOE order manner, something that's so R&D level. And so they stopped, they converted us actually to an R&D project, and then for those 2 years we were reviewed every 4 months by an external technical review committee managed by Oak Ridge. And then that committee reported to Oak Ridge. DOE certainly heard about, and NSF heard about what was going on. And then we had a full DOE /NSF review in December. And I want to thank Chris, Keith, and JLab for letting him come. He was a member of this panel plus this panel, so he's put on a lot of hours. And maybe he'll be a member of the next panel too. We believe we're going to continue. At least the committee seemed to like us. In fact, the committee said that the key technical milestones have largely been met that they set for us to the 2-year period. Being able to produce high electric fields, uniform magnetic fields, small uncertainties in we want to reduce the uncertainties in transporting the helium-3 using the phonons, plus other advances. And let me tell you a little bit. So this is all stuff that sort of happened in the last 2 years. So in 2011, at the time of the review, this is our electric field that we could produce as a function of temperature or vapor pressure. This is the vapor pressure of the liquid. If you're on the saturated vapor pressure, there's a fixed there's an exact relationship between the temperature and the pressure as you walk down this curve. And so here's the temperatures up here, the pressure's down here. What we saw was, oh yeah, no problem. We can get electric fields that are well above what we need, except when we got to superfluid. So the superfluid is around 2 Kelvin, and as we went below that, it was getting lower than the goal, and we didn't know how to extrapolate. It turns out, we want to run the experiment. This is 1.6 Kelvin. This is actually thermodynamics. It's an exponential. If I want to get to operating temperature of 0.5 Kelvin, that's actually 10 to the minus 4. I guess that's over here. So you can draw the curve if you want. I don't know what's going to happen. So that was a concern. What's going to happen to this when you actually get there? So we spent the last 2 years, we developed a new system that we could rapidly open and close cryogenically and change things and try to develop high electric fields in the superfluid helium. There's a picture of it here. Recent data from last summer showed that we actually were able to achieve well above 80 kilovolts per centimeter at any measurable pressure or temperature. In fact, this was limited. We believe this was limited by the leads. they're working on improving the electrode leads, that this was not breakdown in the actual superfluid. And this is at the operating temperature, we were at 100 kilovolts per centimeter. So it looks like that remaining challenge was addressed. However, both this experiment and the previous one were done with polished stainless steel electrodes. As I said, we can't have a conductor inside or any serious. We can have a conducting surface, very thin surface, but not electropolished stainless. And so our next step for high voltage is to produce an acrylic electrode with a thin coating of poor conductor and check its high voltage response. So we have I showed you the medium scale high voltage. We also have a small scale system. That small scale system has been tested with a lot of materials with plastic coatings, and it's worked on the small scale. Now the next test is to see if it works on the scale of about that big. This is a carbon nanoparticle coated on PMMA. And we're learning a lot about crazy plastics, Torlon and PEEK and PMMA. That's the kind of stuff we have to make the apparatus out of because it has to be largely non-conducting. We're also doing magnetic development. This is work in Caltech on building, this is a half-scale coil, cosine theta coil, low field. The characteristic field is about 30 milligauss. There's a superconducting lead shield. It all sits in a cryostat and then is installed into a magnetic mapping system. Actually, the whole mapping system is right next door. You're going to hear in a few minutes from Bicep 2. The Bicep 2 people are right next door. We share cryogenics and hardware all the time. It was great to see their results. And so we use this to measure magnetic fields at cryogenic temperatures. Recent results just last year with the lead shield superconducting, we were able to get gradients, reproducible gradients at the level of 0.2 microgauss per centimeter. If you, SI, yeah, unfortunately, we are at Caltech, tell this about Caltech, we're now using Purcell's new edition, which is SI, and it's driving the faculty crazy trying to teach the students in SI. The book is in SI, and we are still thinking in CGS, so we'll eventually figure it out. The lead shield is a superconductor, so it also improves the magnetic shielding greater than a factor of 100. And the present gradients we have with a fairly elementary external magnetic shield, we're able to demonstrate gradients that are at the level of 4 × 10⁻28 centimeters for systematics. That's if you don't correct. If you know what the gradient is, you can actually correct for this even better, which is this is comparable to the statistical sensitivity goal. So, at the review, how do we continue forward? What's the path forward? The collaboration proposed remaining in this mode of R&D, demonstrating that we can produce the hardest parts of the experiment. So we came up with this lingo, critical component demonstration. It's got a nice CCD acronym. So we use that to allow us to move forward over the next 4 years. What we want to do is we want to build essentially full-scale prototypes of the key hard systems. We want to demonstrate that they can work. In fact, if they work, they're the final system for the real experiment. And so, but the idea is, it's a prototype, meaning the first one you build probably won't work. It'll probably be the second or third that you'll actually do. So it is an R&D mode of operating. So we're building prototypes. Of course, we hope, we anticipate after the 4 years that we'll have a prototype that's good enough for the real experiment. And so the review was in December. Recent status is that NSF, thank you Gail, has approved the 4-year proposal, which we rapidly submitted at her request for $6.5 million of order. We'll talk about the details later. And we anticipate a comparable amount of money from DOE for this 4-year period. And we hope to continue this external committee monitoring us at some level. It's important to point out that we now don't have any milestones. They told us instead to have inch pebbles. It's not a milestone, it's an inch pebble. So it's just to distinguish it. So we have inch pebbles to monitor progress. And we would anticipate following this 4 years that we could complete construction of the conventional, more conventional systems like the neutron beam guide, the general infrastructure, the external room temperature magnetic shield, on a period of 2 years and have the whole experiment commissioning by the end of the decade. And so the idea for this critical component demonstration was to do the hard stuff first. And so these are the systems that we want to attack in the next 4 years. I'm not going to go through them. I have this interesting column here called Technical Readiness Level, TRL. That's something that NASA uses. DOE also has it. They don't use it as much, but we found it quite interesting. Generally, you're supposed to be at 6 or 7 before you construct a project. Our understanding of where we stand on all of these is at 3, 4, 2 in some cases. And so this is where we stand in terms of risk at the moment. This is where we would anticipate being after 4 years in terms of being ready to build the whole experiment. And yes, we do have project management. We have an org chart showing here, which we showed to DOE. And so let me conclude by pointing out that, of course, we're not alone. There is a large worldwide effort to measure EDMs at a variety of laboratories spanning this middle part of the world. And I have, again, a long table of what all the experiments are and their sensitivities. There's about 4 whose eventual goal is sensitivities comparable to the SNS experiment. Some of them are in a preliminary stage, phase 1. And so we do have to compete with those. So why are there so many experiments going? Why are so many people attacking this science? And it's because the science remains compelling even with LHC and after LHC data. The recent NSAC long-range plan implementation report from 2013 said that one of the things the U.S. should do is construction of a high-sensitivity neutron EDM experiment. Of course, right after it, they also said doing parity violating Jefferson lab. I'll put an ad for that in as well. And also, the very recent P5 report, we even showed up in that, saying one of the most powerful probes for new physics at the more than 100 TeV scale is neutron electric dipole moments. So there are exciting opportunities for both new and existing facilities to attack this. This table sort of summarizes how we stand. This is sort of this experiment, this one, and this one, plus us, are sort of the experiments attacking the ultimate sensitivity. And this shows some of the capabilities that are built into the experiments. Some of these capabilities are it's good to have different capabilities because it'll undoubtedly lead to different systematics. But in a few cases, we believe we have unique capabilities, no, yes, that will allow us to attack some of the systematics. We believe we are unique in that regard. So let me wrap it up. I hope to convince you that EDMs remain important in attacking beyond standard model physics. And this is recognized worldwide. There are new technologies that are being used to push this limit by a factor of 100. And we believe certainly that this SNS experiment is world leading in terms of statistical and systematics.
Questions?
Is that Roger?
I can shout. Fred,
Yeah.
at the end of the decade, you're doing commissioning. Is that with BEAM, and does that mean that at the end of that, you plan to have that 3 years of running and get to that goal? Or
Correct.
is there...
Correct. The commissioning is undoubtedly there'll be, in fact, commissioning and data taking will be mixed. So you could add 3 years to that to get a final sensitivity at that level. None of these experiments have ever lasted that short a time. It'll probably be 10 years of data taking to actually sort through whatever we find, whatever new physics we find. If we find it with one technique, we will use that other technique to confirm it as well. In fact, we'll probably use both techniques anyway to minimize systematics.
Just one other thing, you're switching beam lines. You want to switch beam lines to the one of the MPD gamma guys.
We are already approved to do that.
What was wrong with the old one?
The flux was too low. There's an issue. There's a monochromator that it was used and it wasn't delivering. And we also realized that we could get even more flux than the original one had. And so it's statistical sensitivity. I should point out we can move the experiment farther down the road. They're talking about another target station at SNS that could give us a factor of 20 neutron increase, which would be a big deal.
Any more questions?
Your lead time is, as you showed, 6 years. Now, then you start making the measurement. But in 6 years' time, technology will have greatly improved. And then at that moment you say, well, maybe I should do it now all differently. What about that?
The danger, yeah, and in fact, we have some of that, because when you're in this R&D phase, we see something, in fact, we're doing that in the magnetic shielding. We're saying there's new technology out there. And so at some point, we have to make a judgment that we have to stop and take the technology that we have. But we have this 4-year period where we can adapt, and we will continue to do that. But after that, I think after the 4 years, we're then locked in. And then we have to build what we say we can build. But you're right, this could go, we don't want this to go on forever. We have a well-defined plan, and so that's the goal.
Assuming you see nothing, what are the prospects for covering the remaining 4 orders of magnitude?
Yeah, so we believe systematics are hard to predict. So we think we could probably, once after the learning process of this experiment, get down another factor of 10. The factor of 10 in statistics requires a very intense neutron source. So we need a factor of, so I said we get a factor of 20 with an upgraded SNS. They're also talking about in Europe a new spallation source, and there's a program that they're trying to develop to put an EDM experiment on that, which would potentially get another. So that would get you sort of 10 to the minus 29. Getting to 10 to the minus 32, I don't know how to do the last 3. We'll take it in steps. So I think there's a path to get 3 orders of magnitude. I'm not sure about beyond that.
All right, let's take our speaker again. So our next speaker is Chris Sheehy, and he will be telling us about the detection of B-mode polarization on the BICEP2 experiment.
Yes, that's right. Hi, I'm Chris Sheehy from the University of Chicago, and I'm here to change the subject to cosmology. So this is the paper that everyone is talking about, detection of B-mode polarization at degree angular scales by BICEP2, and I will get into what that means. We are a relatively mid-sized collaboration, especially compared to other large like satellite experiments that you probably heard about that measure the cosmic microwave background. Mostly at Harvard, Stanford, Caltech, and the University of Minnesota. This is one of our group meetings. So I think I should give a little summary of cosmology in a nutshell, enough to give you an understanding of what B-mode polarization is. So probably heard the universe expanding in accordance with Einstein's general relativity. So if the universe is expanding now, that means that at an earlier time, it was smaller and denser. And so when the universe was smaller and denser, it was also hotter, much hotter. And so from that time, from that era in the early universe, from t equals 0 to roughly 300,000 years after the Big Bang, the universe is hot and ionized. And we can see that ionized plasma of the early universe in the form of the cosmic microwave background. So this is a schematic that you probably see pretty often in popular publications. So this is us now. These are stars and galaxies. And we would say stars and galaxies, these are density perturbations in the universe. So when you hear the word density perturbation, that's all we're talking about. You know, I'm denser than the air is denser than interstellar space. And so if the universe is expanding, then it was smaller at some time, and eventually all this matter gets compressed together. And these density perturbations still exist, but during this time there are no stars, there are no galaxies, they haven't formed yet. So this is going back in time as we go to the left. And here, the universe is hotter and hotter and hotter, and eventually the universe, as you go back in time, gets so hot that all the matter in the universe is in the form of an ionized plasma. And so we can look out from our vantage point in one of these galaxies and look out in any direction and see this ionized plasma that is actually very opaque to light. So in the early universe, between t equals 0, the Big Bang, and 400,000 years after the Big Bang, this is completely opaque to light. And so light in the early universe scatters off the free electrons in this plasma. And at the time, we call it recombination. The temperature drops to the ionization temperature of hydrogen. And all the photons that are getting scattered around by the free electrons then free stream out in all directions in the universe. And so we can see it. So the density perturbations that are here now still exist at the surface, still exist in the universe at this time. And we see those in the form of the cosmic microwave background. So this is a full sky map made by the Planck satellite of the cosmic microwave background, the unpolarized cosmic microwave background. This was first detected in the 1960s by Penzias and Wilson. And so these little hot spots and cold spots are overdensities and underdensities in the early universe. So where do these density perturbations come from? Well, the reigning theory is inflation. So this has been popular since the 1980s. And my usual answer to how does inflation cause density perturbations is ask your local theorist. But I'll try to get a picture here. The idea is that before the Big Bang, there are quantum fluctuations, there are quantum fields, and in particular, there's a postulated inflaton quantum field. And inflation, whatever drives it, takes these quantum perturbations and blows them up to macroscopic scales. And so that inflation then is the source of these density perturbations. Now in some sense, we know these density perturbations have to exist because we know that the universe isn't smooth. But if inflation is the true mechanism that caused these density perturbations, it also does one other thing. It takes fluctuations in the gravitational field before inflation and blows them up into gravity waves. We would call these tensor perturbations. If the density perturbations are scalar perturbations, then gravity waves are tensor perturbations. And that's what BICEP 2 wants to see. So this would cause polarization of the cosmic microwave background. So the CMB, the cosmic microwave background, is polarized. This has been known. So this is not a full sky map. This is about a 5 degree by 5 degree patch of that full sky map. And the polarization, so these are the little overdensities and underdensities. And this was found to be polarized by the DAISY experiment in 2002. This is another South Pole experiment. So we can represent this polarization as a vector field laid on top of the hot and cold spots of the CMB. So the CMB is polarized in a very mundane way. There's the polarization that BICEP 2 has measured, but there's the polarization that's been known to exist for the last 10 years is formed as a standard consequence of the standard cosmological model. So let me see if I can explain why the CMB is polarized in this mundane way. So this is just a little schematic of the early universe that is ionized. So you can forget the protons, you can forget the ions, and just think of these electrons in the early universe plasma, so say 300,000 years after the Big Bang. These have a really high scattering cross-section of photons. You've got photons bouncing around, scattering off these electrons. Now, because the early universe isn't smooth, there are overdensities and underdensities, you've got a matter overdensity here. And we would say that the photons and the baryons are tightly coupled. You might have heard this before. We say it's tightly coupled because the scattering cross-section of the electrons is so large for photons that wherever there's more baryons, there's also more photons. So when you get an overdensity, you get a conglomeration of photons, an overdensity of photons. And what happens is, because you have an overdensity of photons, you get diffusion, photon diffusion, out of these overdensities. And so if you're an electron sitting outside this overdensity, and you're seeing this photon fluid diffusing out at you, you're seeing flow, photon fluid flow. And the crux of this is that the flow isn't just uniform. There's gradients in the flow velocity. And so as the photon fluid is moving away from these overdensities, it's not moving at the same speed everywhere. So now if you're an electron sitting in this flow, you see diverging flow or converging flow somewhere in the field, or somewhere in your vicinity. And so if you're seeing diverging flow here, the photon fluid is moving fast away from you there. And here the photon fluid is moving very quickly towards you there. And so what you end up seeing is a net red shifting of light and a net blue shifting of light, depending on where you are in the radial direction, how far away you are from this overdensity. And when you see, I don't know where these Z's came from, when you see this red shifting and blue shifting, it always occurs in the radial direction. There's no red shifting or blue shifting perpendicular to this overdensity. And so the light that gets scattered off these electrons, it gets a net polarization. And the key thing here, the key thing here is that the net polarization is always aligned with the radial direction or perpendicular to the radial direction. It's never at any other orientation to the radial direction. And so if you take those hot spots and cold spots, so you take these overdensities that are the hot spots and cold spots on this map, and you just stack them up, like take the map with the CMB and just take every hot spot and every cold spot and just stack them together. And then plot that vector plot over the stacked map. You get this pattern. And you'll see this is the hot spot. The color scale here, it doesn't matter, but you could imagine just laying these vectors on top of this plot here. And the vectors are always either perpendicular or parallel to the radial direction. And we call this an E mode. So if you've been hearing about E modes versus B mode, this is all an E mode is. It's just a vector field that's got no curl. So it's an analogy to the electric field. And this is just predicted to exist by standard early universe models. And we know it exists. But what BISA 2 wants to measure is the B mode polarization of the CMB. And the B mode polarization of the CMB is predicted not to exist in any standard early universe models. So, what might cause the B mode polarization? The answer we're hoping for is inflation. So let me just say something about how inflation might cause B mode polarization. It's not that inflation per se causes B mode polarization. It's that gravity waves in the early universe cause B mode polarization. So this is my schematic of a gravity wave. The idea is as the gravity waves, well, I played it a second ago. If you have a gravity wave, that's traveling in the z direction, then in the transverse direction, the gravity wave stretches and compresses space-time as it travels. So if you're now one of these electrons sitting outside this overdensity, and a gravity wave passes by, it's compressing space-time, or stretching space-time, around some electron here. And if it compresses space-time, the electron sees a blue shift. If it redshifts space-time, if it expands space-time, the electron sees a redshift. And this is the same anisotropy. This is the same redshifting and blue shifting that causes the E mode polarization. Except these gravity waves don't know anything about where the overdensities are, so they're all in random orientations. So if you've got gravity waves at the same time in the early universe, it's going to create E mode and B mode polarization. So it's really the E modes that are special. The gravity waves just produce everything, E modes and B modes. And so this is what we're trying to detect. The question is then, why does inflation produce gravity waves? And one of the guys said it. But detecting the B mode polarization of the CMB would be a dramatic confirmation that inflation is the correct paradigm. Okay, so what we're actually going to go measure is the power spectrum of the cosmic microwave background. So I should probably say for a minute exactly what that is. So this is the same all-sky map of the unpolarized CMB fluctuations with hot spots and cold spots that was detected in the 60s and recently measured with very high precision by the Planck space satellite. And so this is the power spectrum of this network. And so we plotted as a function of multipole L. And this power spectrum peaks at L of 200, which corresponds to roughly degree scales. And degree scales, it's roughly 2 full moons on the sky. So these hot spots and cold spots, the average size of these patches is about was about a degree across. And so this power spectrum that we talk about, multipole L, it's basically, it's analogous to a Fourier decomposition on the sphere. You have different modes, and you stack them all up, and as you stack these modes up, yes, as you stack these modes up, you can make any field on the sphere you want. This is the power spectrum stepping through, and this is showing that the peaks of degree scales. And so this structure here is just can be decomposed into these so-called spherical harmonics. And that's as you have high L, these are small scales, and low L are large scales, just like Fourier modes. So this is the unpolarized power spectrum. This is the prediction for the standard E-mode power spectrum. And these are the B modes. So I might have lied a second ago when I said that only inflation causes B modes. The E modes is a very special pattern. And so anything you do to distort this pattern will make it not a pure E mode. And so we actually observe this E mode polarization through the intervening matter of the universe. And so if the early universe that we're looking at has this E mode polarization, as it gets gravitationally lensed by galaxies and galaxy clusters between us and the early universe, it turns that E mode into a B mode. And in fact, this is the solid line. We call it the lensing B mode. We know it's going to be there. It's starting to get measured with high precision, but it's not what we're after. What we're after is this curve here, the dashed curve. This is the prediction for an inflation gravity wave background generated B mode polarization. And we parameterize the peak. We parameterize the amplitude of the spectrum with R. R just sets the relative amplitude between this spectrum and the scalar spectrum, or the E mode spectrum, I should say. And so this was the state of affairs in early March. These are predictions, or the curves for different values of R. And up until bicep 2, it was all upper limits. These are the lensing B modes that have been measured by others' experiments. But bicep 2 really wants to push down and measure in this region here. So, how is bicep 2 supposed to measure B modes? So bicep 2 is a very, very simple experiment. I mean, it's not a simple experiment, but it's a simple design. This is a telescope, and it's quite small. It's about this high and this far around. So a 30-centimeter aperture. It's just a refracting telescope. You have a lens that focuses light down onto the focal plane here, to the camera. There are much larger telescopes, but because we only care about this large-scale degree structure, we can have a small telescope with relatively poor resolution and still have the same sensitivity to these degree scales. And the smallness of this thing gives it certain key advantages. So this is the bicep 2 telescope on a mount in the Caltech High Bay, next to apparently EDM experiments. One of the nice things is we can take the entire telescope and put it on this mount and put it in the high bay and do all sorts of calibration measurements on it before we put it in the field. This is actually a liquid helium cryostat, so the entire telescope, optics and all, is cooled to 4 Kelvin. And we can, so larger telescopes, all the detectors have to be cooled to cryogenic temperatures. For this, we can cool the optics. So it's great for systematics. So then we take the telescope and we ship it down to the South Pole. So this is where the bicep 2 telescope goes, and it's in this ground shield. You can't see it in here. This ground shield protects the telescope from stray light coming in from the ground, which could otherwise be systematic. This is the South Pole telescope right next door that photobombs us all the time. And it's a much larger telescope, and it can do these small-scale lensing B modes, and it's really good for that. But in fact, our much smaller telescope is just as good for degree scales. It's just as good for these large scales. And so There it is, on the ice. And the South Pole is a particularly good place for doing these observations because it's high and dry. So, all of Bicep 2's observations are at a frequency of 150 gigahertz. So these are centimeter wavelengths. And so when you look out from the ground at centimeter wavelengths, the main thing you're seeing is water and oxygen rotational lines in the atmosphere. So if you can get to a place that's very high and very dry, it is ideal. Paradoxically, it's also, the logistics are very easy at the South Pole. Other experiments try to do this and do this from the Atacama Desert in Chile. But it's actually very difficult to get to get supplies into the Atacama. Here there's a National Science Foundation station, and they deal with everything. So we fly in on ski-equipped LC-130s, and they have power waiting for us and meals, and we don't have to worry about anything except for the science. And so we go there in the summer and set up. We spend about 3 months at a time, and then we leave. And we leave behind a winter rover who stays for the cold 9-month winter, and there's no in and out, the planes can't land. And the winter rover gets to see this. I've never seen this because I've never wintered. But it's a beautiful sight, and the atmosphere stays very stable for the 9 months of the polar night. And this is an ideal place to do CMB. So Bicep 2 is actually a progression of experiments from the South Pole, mostly worked on by the same people. So this is Bicep 2 here, but you can see there's a whole progression. All these experiments share very similar optics, very similar experimental strategy. The main difference between all these things is the number of detectors. These are pixels in the focal plane, So here's the Bicep 2 focal plane, and each one of these little guys is a pixel. And so getting more detectors on the sky simultaneously gives you more instantaneous sensitivity. And that has been the main difference in this progression of experiments. So I should probably say something about the actual detectors that we use. This is the focal plane that light's focused onto. And you can see each of these are tiles. These are photolithographed tiles, so made in a fashion very similar to how you would make a semiconductor chip. So blowing that up, this is 1 pixel. And this has polarization sensitivity because it's composed of a whole bunch of sub-slot antennas. The power from the optical power that's incident on these slot antennas is summed coherently and then deposited on what we call a transition edge sensor. The transition edge sensor is pretty cool. It's cooled to its critical temperature at around 300 millikelvin. And so it stays right on the superconducting transition. And any tiny bit of power deposited on it changes its temperature and therefore its resistance. And since the resistance in this transition region is a very steep function of temperature, it has exquisite sensitivity to the incoming power that's deposited on it. Bicep 2 then multiplexes the signal from these transition edge sensors and reads them out via squids. So we get parabolic fields as well. But the polarization sensitivity comes from the fact that these slot antennas are all either horizontally or vertically aligned. And you can see the slot antennas here are interleaved in between each other in the same pixel. So we get dual polarization sensitivity in 1 detector. And so this is the Bicep 2 focal plane now projected onto the sky. So this is about 30 degrees by 100 degrees. So a patch of the sky that we relentlessly observe from the South Pole. And each one of these detectors is in fact 2 detectors, a vertical polarization and a horizontal polarization detector. And we measure the polarization of the underlying CMB by differencing the signal from these 2 detectors. And so we take the Bicep 2, we take the telescope, and we scan it back and forth on the sky for 3 years. And so this is not Bicep 2, this is the Keck array, one of the experiments that is now operating that's come after Bicep 2. And this is during the day, obviously, but This is just what BICEP 2 does for 3 years, observing the same patch of sky and getting more and more and more sensitivity. This is what the raw data looks like. This top panel, so that the x-axis is time. It's roughly 1 hour's worth of data. This is the telescope scanning back and forth. This is azimuth on the y-axis. This is taking the two dual polarization detectors and summing them. If you sum those two detectors, you get a measurement of the unpolarized CMB. And what you're seeing here mostly is atmosphere. So you can imagine as the telescope scans back and forth, it might scan over a cloud and it picks up some signal. That signal averages down, but it is a significant noise component. But the atmosphere is completely unpolarized. So when you difference the signal, any sky signal, any atmospheric signal cancels away, and you'll have a nice, clean polarization time stream. And so then, we do this for 3 years, and because we know where the telescope's pointed, we can take this data and we can bin it into map pixels. And so binning 3 years of this data into map pixels, this is what we get. So we measure the same unpolarized cosmic microwave background intensity that other experiments measure. But then we get measurements of the polarization. Now, I haven't explained what Q and U are. These are the Stokes parameters, but this is just another way of representing polarization instead of a vector field. I'll go back to vector fields in a second. And so if you're an expert, you can already see very high signal-noise structure in here. This is the standard E-mode polarization, and one can just know that the horizontal vertical pattern and diagonal pattern here is the sign of E-modes. The sign of B-modes would be reversed from this. To check for systematics, we can make a different set of maps. Instead of binning all the data into one final map, we can bin into subsets of maps. So one of the things we do is take the first half of our data, the first year and a half, and bin that into a map. And then we take the second half of our season, the second year and a half, and bin that into a map, and subtract the two. And if there's no systematics, then when we subtract the two, all the signals should cancel, and we should be left with something that's completely consistent with noise. We refer to these as our jackknife tests. And so we do that, and we get maps that are very clean, and in fact, these are consistent with noise. We do this for all different kinds of splits. We can split via detector set, we can split via other subsets of time. Most systematics we can think of, we can form a jackknife that it will fail. And so we do a lot of these, and they all look good. So this is the polarization signal, represented as a vector pattern now. So note the size of the vectors, 1.7 microkelvin. This is the E-mode polarization. What we're interested in is the B-mode polarization. So the B-mode polarization, relative to the E-mode polarization, looks like this. So it's very small. So if we blow up the scale now, we can see the B-mode pattern. And this is BICEP 2's fundamental result, is this curl pattern. So these are the power spectra that BICEP 2 makes corresponding to these maps. This is the unpolarized CMB power spectrum. This is the E-mode power spectrum that BICEP 2 measures. These are all measured with incredibly high signal noise. I know the y-axis here is pretty large, but these error bars are very tiny. The red lines, the red solid lines, are the standard predictions of the standard, we'd say, lambda CDM cosmological model. And in every case, except for BB, the B-modes in this panel, the data falls right on the solid red line. So there's an excess here. So let's zoom in on the BB panel. This is a prediction for R of 0.2. And I know we haven't done any fitting yet, but plotting it for reference. And so the excess here over the standard cosmological prediction is 5.2 sigma. So it's very high significance excess. So how do we know that this is real? I won't go in. We've done very careful systematics checks. One of the things we do is beam mapping. This is bicep 2 at the South Pole. There is a microwave source here on this building over here. It's very difficult to see. Bicep 2 can't observe it directly because it's in this ground shield, so we put a flat mirror on top of it. And we know what each of our detectors' response is as a function of angle. And so this is one of the reasons that a small telescope is good for systematics. We have cross spectra. So I can take the bicep 2 signal and I can cross-correlate it with the signal as observed by other experiments. Now, bicep 2 has detected this signal for the first time, but in cross-correlation with other experiments, the significance can actually be high. So this is a predecessor. So these black points are the bicep 2 points that I've shown. These X's here are the cross spectrum, which is just basically a cross correlation, of the bicep 2 signal with the predecessor experiment, bicep 1. And there's a 3-sigma detection of the same signal in the predecessor experiment. I should note that the predecessor experiment used quite different detector technology and should have a very different sorts of systematics than bicep 2. We've also shown data from a experiment that has followed bicep 2, the Keck array, and these are these blue points here. These are preliminary data. The Keck array data is coming soon, but the fact that this experiment appears to see it following bicep 2 played a large part in our confidence that what we're seeing is real and on the sky. So cross-spectrum with other experiments is a very powerful check that what we're seeing is not systematics. One of the other things to think about is galactic foregrounds. So bicep 2, instead of looking at the whole sky, looks at this little patch of sky. This is the bicep 2 field here, overlaid on the entire sky. And what we want to avoid is all this contamination from the galaxy, all this stuff that's in our own galaxy that's between us and the cosmic microwave background. And so we choose this patch of sky to be very clean. And so the question is, how much polarized galactic contamination is there in our field? And this plot appears in the paper. There's all these different models of what polarized foreground should be in our field. Here we've chosen a subset of them, but they all tend to predict that contamination from the galaxy is at a very low level. And so we think it's very unlikely that foregrounds could contribute power at the level that we're seeing. We can also say something about the origin of our signal by the cross-correlation with the other experiments. So in addition to being a check against systematics, because the predecessor experiment, bicep 2, bicep 1, was at a different frequency, and because we expect foreground contamination to have a different frequency spectrum, different color, than the cosmic microwave background, we can discriminate between cosmic microwave background signal and foreground contamination by requiring that the spectrum that we make at different frequencies have the correct amplitude to be CMP. And so we do this constraint with the cross-correlation of bicep 1 at 100 gigahertz and bicep 2, which observed at 150 gigahertz. And it favors a CMB spectral index. The CMB spectral index on this plot is minus 0.7. If the signal were dust, the spectral index would be around 1.7, and if the spectrum were synchrotron radiation coming from the galaxy would be around -3. And so it favors a CMB spectrum. The likelihood of a dust spectral index or a synchrotron spectral index is low, but it's rejected at only around 2 sigma. So it's not significant. It's not very significant, but it seems to point to a CMB origin. So if it's not systematics or it's not foregrounds, then we just fit an inflationary gravity wave spectrum to our data. We have R of 0.2, which is significantly higher than most would have thought before this result. The excess over the standard prediction was at 5.2 sigma. But if we assume an inflationary gravity wave model, we can rule out R of 0. We can disprove the null hypothesis at 7 sigma. Anything that adds extra signal here that's not CMB will, of course, decrease the significance, but it seems unlikely that something could be that large to really do it. Right, so this is showing the constraint on R under different foreground projections, different projections of how bright the galaxy would be in our field. And the black line here is the base result. So the likelihood of the tensor to scalar ratio in R peaking at 0.2 and falling to 0 at 7 sigma out here. If there are galactic foregrounds, it takes these likelihoods, and you have to subtract that foreground now from these data points and refit, and it shifts the likelihoods over. For all the models that we consider, and this is really what the state of affairs looks like, the likelihood of R of 0 is still very, very small for all these models. I will note that it is difficult to assess the probabilities that any one of these models is actually correct, and we call the model actually quite driven by data, WMAP data. WMAP is a CMB satellite prior to Planck. But they're driven by information. There is information about polarized dust in the CMB, and that is used in making these models. So, where we're at is we're going to continue to map the signal with higher precision. And perhaps most importantly, we're going to continue to map it at different frequencies to try to disentangle CMB from possible foregrounds. So the Keck array is currently observing now. It is the Keck array is currently observing, so each of these telescopes is like 1 bicep 2. So Keck array should have about 5 times the sensitivity as bicep 2, and it's observing now. We have 2 receivers in the Keck array at a different frequency than bicep 2. And the maps made from this are already at the sensitivity of the maps made from bicep 1 at 100 gigahertz. And so the sensitivity of this thing, to improve this plot, we want to tighten this plot up, the spectral index constraint. And we already have the sensitivity with this next experiment where we can reproduce this plot with the same sensitivity. And this is from 2 months worth of data. And so very soon we should be able to redo this plot with a much tighter constraint. We can also cross-correlate with a different experiment. This is the South Pole Telescope that is right next door to bicep 2. It will put in a polarized receiver with more sensitive and more frequency channels very soon. It also has frequency coverage right now. And so potentially we can cross-correlate these signals to say something about the level of foregrounds. And the Planck satellite. So I showed you maps from the Planck satellite, but those were unpolarized maps. Planck has not released their polarized data yet. Planck will have a lot of frequency coverage over the full sky. And so when Planck releases their results that are due out this fall or winter, they might have something to say about foregrounds in our field. And although they might release a paper near, I've been hearing rumors, 3 weeks being tossed around that they'll have a paper that'll say something about foregrounds. It's unclear. The very latest, though, Planck data products have to be out by December. And so once December rolls around, Plonk will have maps, and this should hopefully shed some light. Thank you very much. I'll leave this up.
You seem to have a good case that it's not dust, but why are the Plonk guys rattling that chain so hard? Sour grapes or what?
So you've been reading blogs. Well, actually, Plonk is pretty silent. They don't really say much. There are people who've done a reanalysis of some of the of one of these models, I should say. Right. Right. So you're probably referring to this is the Raphael Flauger paper. So yeah, they've taken issue with DDM2, this one model. They've said so. So this model DDM2, right? These are all sort of pre-Plonk estimates. Plonk has not released their polarization data, but they did put out these top slides in PDF form. And this was actually, we were, thinking it was the best information available. We wanted to utilize it. They've taken issue with some of the analysis done from this PDF slide. They pointed out that the actual uncertainties involved in doing this are quite large, and so DDM2, could have more uncertainties than you think. But the rest of these models are completely unchanged by all this. So that's the issue.
The polarization mechanism with gravity waves inherently produces linearly polarized microwaves. You must have looked at the V Stokes component.
Oh, yeah. So
how much circular do you see?
So BISEP 2 can't measure circularly polarized light. None of these experiments can. And so the answer is we don't know, but the CMB is expected to have no circular polarization.
Yeah, I know, but that's a nice cross-check, right?
Yes, it would be if we could do it, yeah.
Actually, it's again about this slide. Wouldn't you say that if you have a new dust map by Planck, you could actually get the R to a more reasonable value? Because you said 0.2 is large.
Certainly, like people, at some level, that this is a combination of cosmic wave background, lensing, and galactic foregrounds. And the question is how much galactic foregrounds there is. It sort of depends on what you mean by reasonable. I don't want to put priors on what I think a reasonable R should be. The fact that people are surprised is a fact, but I don't know if that's reasonable or not. It's probably for other people to say.
My understanding, you decompose of your background over a set of partial waves, and you employ huge amount of partial wave, several hundred of partial wave.
Partial wave?
This partial wave, multiple, what you show.
Multiple. Okay.
Multiple, okay, it's just terminology.
Yeah.
Multiple. My question is, what you are doing to avoid inevitable ambiguity, disentangling this huge amount of partial wave? Allow me to explain a bit. In this laboratory, we routinely employ partial wave analysis or multiple decomposition, if you want, for analysis of photo and vector production data. If we have several tens partial wave, we have considerable problem with ambiguity. Instead, in your case, several hundred multiple, you have pretty small error bar for multiple with L less than 100. What you are doing?
I'm not sure what you mean by ambiguity.
You have correlations for it.
If you have
partial
wave in some angular distribution, you have many possible ways.
Yeah, okay.
Anybody would describe this data with different weight of different partial waves.
Okay. what are we, I'm not sure that, you're not just talking about the loss of information from the power spectrum, right? Okay. Ambiguity in the sense that of like mixing between different modes.
Yeah, simply the coefficients of the spherical harmonic decomposition.
Exactly.
But there's
That the
only
error
5
bars
that
would
way.
get, could get large.
Okay, so we completely, all right, so I should say we completely account for all of this via a very sophisticated Monte Carlo approach, where we take bicep 2 instrumental noise and we simulate it at the time stream level for 3 years of data, and then we have random realizations of cosmology, and we add the maps together, and we can treat our power spectrum analysis as a black box in this sense, because when we subject our simulated data to the spherical harmonic decomposition, any mode mixing, any ambiguity, we measure it all via the simulation procedure. So that's how we would account for anything like that.
Okay, how many pixels are in the Planck map, roughly?
Good question.
I mean, because
12
going out,
times 2048 squared.
fine, so then going out to 1,000 in the multipole is not that far, given the number of pixels that you've got available.
Okay, we don't go out to 2,000. We only publish up to 350.
Fine, but I mean, the map you showed from the Planck went out to 1,000. right?
Sure.
Or 10, 20.
That's also much. So
Yeah, so I'm just saying, talking to Victor really, that you've got so many pixels that doing a decomposition out to 1,000 spherical harmonics in total, of course, that's 1,000 total orders. It's not 1,000 in each of the 3 coordinates.
mm-hmm.
So it's only like 10th order in each coordinate, right?
I suppose. Yeah, I mean the main thing that sets how high in a multipole we can go out is the size of our beam, because we suppress all power at small angular scales because our response of the telescope is about a degree. So any structure at sub-degree scales we just can't see, and it's completely suppressed. So we end up not worrying about it.
All right, one more.
Yeah, I actually asked this question about a month ago to some other people, but let me try it again. The question about the influence of the Planck data on the result, it's really a question of the uncertainty in R. And I wasn't, have you refined the components of the uncertainty to say how much smaller your error bar will get in R once you have Planck data, for example?
No, not once we have the Planck data.
Because it will narrow the model range, and then you can, in principle,
Yeah. So in the paper, we didn't
separate.
marginalize over
Right.
foreground estimates because it's very difficult to parameterize which of these models is correct. Presumably with Planck, when they release their maps, then we'll be able to do something robust. But it is unclear though what the uncertainties of the dust level Planck will be able to, what constraints Planck will be able to put on the foreground center field. They're a full sky experiment, so they have roughly the comparable sensitivity to R, to inflationary B modes, but it's over the full sky, averaging all the modes together. We care only about our tiny little patch, and in our tiny little patch, the Planck maps are actually not going to be particularly deep. So what we'll do is try to use the Planck 350 gigahertz maps at a frequency where dust is actually incredibly bright. We observe at 150 gigahertz where dust is dim, but you can observe at other frequencies where dust is bright. And so, I don't actually know what the projected sensitivity at 350 is going to be. It could be something marginal where it's not quite as constraining as we might hope. But I should say that once Planck releases their data, even if Planck themselves have a more ambiguous result on that, cross-correlating the Planck 350 gigahertz maps with our own data, when the actual data becomes available, will be a very powerful thing to do, with Planck doing.
All right, let's thank both our speakers again. And we reconvene at 11 o'clock.
spectroscopy, understanding extended baryon resonances, result from polarization experiment with glass.
All right, thank you, Eugene. I'd like to thank the organizers for inviting me, and it's my pleasure to talk about the baryon spectroscopy program here at Jefferson Lab, or not only here at Jefferson Lab. So I'll briefly motivate probably some people that haven't heard it in the room yet. I talk a little bit about the motivation here for complete experiments, and then I will concentrate mostly on the production of single pions and 2 pions in photo production, and give you a flavor of recent results and what we actually learned from these polarization measurements. Okay, like a brief motivation, QCD is a theory of strong interaction, we all know that. But when we talk about excited baryons, we're talking about non-perturbative QCD, and there is no access to QCD directly from first principles. We also know that quarks are confined within hadrons. And so the question that we want to answer is, how does QCD actually give rise to excited hadrons? And we can break that up into a few more questions. What is the origin of confinement? We know that quarks are confined within hadrons, which is particularly true for excited states. How are confinement and chiral symmetry directly connected? And would the answers to these questions explain the origin of about 98% of all the matter, the observed matter in the universe? So when we talk about excited baryons, there's still some open questions about the structure of these resonances. So in the naive quark model, we can picture the baryon as an object of 3 constituent quarks. There's also the possibility that we have flux tubes, and in light of the Blue-X talks, there may be gluonic excitations also within baryons. There's also still the possibility of some sort of quark-dipole clustering within the baryon, giving rise to somewhat fewer states than what we expect from the naive quark model. And there's also the possibility that baryon resonances are maybe dynamically generated, so we have some sort of interaction between mesons and the ground state nucleon. And probably the answer to the question, what is and what are excited baryons, is somewhere in between, and maybe a composition, a linear combination of many of these pictures. Okay, looking at the spectrum of baryons, this is a somewhat outdated plot now, but it still shows the features. So we have the ground state nucleon down here, the well-established state. The particle data group classifies baryons with a star assignment according to how well they are established. So 4-star state is a well-established state, and then 1- and 2-star resonances are like weakly established state, like where we have no real solid evidence whether these states exist or not. So we have the ground state here, then in the first excitation band, using the harmonic oscillator model, then with negative parities here, where we have, well, baryon can be described by 2 oscillators. So in this case, we would have 1 unit of orbital angular momentum here, and that gives rise to a doublet with spin 1/2 and a triplet with spin 3/2. And these are predicted here, the blue lines are predictions, and there are well-established resonances that correspond to these predictions in the quark model. However, in the second excitation band, the trouble already starts that we're missing states. In the second excitation band, we have the radial excitations, or the case where 1 oscillator can have 2 units of orbital angular momentum, or we can have the case that both oscillators carry 1 unit of angular momentum, and then these 2 can couple to overall spin 0, 1, and 2. And it appears at the moment that the first 2, the 56 plats, are actually completely filled, not only looking at the nucleons, but also at other baryon resonances. And there are others missing here in these other multiplets, and that has given rise to some speculation that some of these multiplets may not exist at all, and that there's some other things that we don't understand yet that may suppress these states. The other possibility is that we simply haven't found them also for that reason. We're doing the experimental program, among other things, here at Jefferson Lab. Okay, for decades, the list of resonances in the particle data booklet has not changed. However, that has changed in 2012 with the new additions of the decades. There have been additions to the resonance listings. So in particular in the 1900 region here, there have been resonances added with even with a 3-star assignment here, whereas other resonances have been taken out. And also what has happened in the latest edition of the nomenclature for baryon resonances has changed. So up to 2010, they were still classified with a partial wave in which they were found in the pion nucleon scattering experiments, where most of our information about baryon resonances actually comes from. So that has changed, and this nomenclature doesn't make sense for photo production anymore. So I would like to draw your attention to this resonance, for example. It's a 3½ plus resonance with a nominal mass of 1900. That has been upgraded from a 2-star state to a 3-star state. So we see clear evidence for the existence of this state, in particular in recent class data in strangeness channels. So here's the results I'm referring to. So we're looking here at the polarization transfer using data that have a circularly polarized photon beam. And here we're looking at the polarization transfer from the circularly polarized photon to the recoiling hyperon along orthogonal axis in the scattering plane, labeled Cx and Cz. And what you can see here on the left side, so you see the open circles are the result for Cz. The solid circles here are the results for Cx. And on the left side, you see the results in the interpretation of the Bonga-China partial wave analysis machinery. On the left side, without this additional P13 resonance. On the right side, with this resonance included. And for example, in this range here, you see there's a clear improvement in the description if this resonance is included. And this is for the lambda channel here. So there's clear evidence that this resonance is actually needed by these class data. So that was a few years ago. And the other remarkable thing is that this group of 3 resonances forms like a triplet of states, and that requires, according to some classification scheme, that both oscillators are incited inside the baryon, which sort of rules out some naive quark-dipole oscillations, or that there is a quark-dipole structure in the nucleus. That has also solved the puzzle for a long time. We've seen the second bump in the K-lambda cross-section. There have been many ambiguous interpretations of these data, and I think it's dominated by this P13 resonance, which is based on the new polarization data that came out of class. So just to highlight what else we have in the strangeness sector. So for example, from the recent double polarization measurements of Frost experiment, we can also measure the target asymmetry. And I've shown here on the left side, this is the case for lambda, K plus lambda production, on the right side for K plus sigma production. And then here we have they're all in the mass range roughly of 1900. This is just a snapshot of what we have. We have data almost from threshold to all the way to well above 2 GeV, but it's quite a hard time to show you the full plethora of data that we actually have. So this is just a snapshot. The target asymmetry, then essentially the case for the target recoil polarization transfer for Tx, so orthogonal to the scattering plane, and in the scattering plane here, and the same is true for the sigma channel. And then on top of that, you see a blue curve here, which is the old K-on-Made model, and then the purple curve represents the latest Bonga-China solution, which also included the P13 that I was talking about on my previous slide. So what we see here is that the curves do not describe the data very well, so there's still a lot to learn, and we're all hopeful that more resonances are required to actually properly describe these data. I think there's no question about that. Okay, so for completeness, I'm also showing the spectrum from the lattice here. The lattice also predicts many of these resonances. and the level counting from lattice calculations is consistent with the non-relativistic quark model. So these resonances are expected, and we're going to find them with our data. What I find also, in light of the recent COAX talks, what I find intriguing is the question whether there are also gluonic excitations in the baryons, and there are indications from recent lattice calculations that there actually are. And what's even more amazing is if we try to subtract the quark masses, so for the mesons we can subtract the rho mass, and for the nucleons we can subtract the nucleon mass, then we see that we roughly get the same, that we get a common scale for roughly 1.3 GeV for gluonic excitations. This is really, really exciting, although it will be really, really hard to identify gluonic baryons experimentally, because they do not have these exotic quantum numbers that we always discuss for meson spectroscopy. Just briefly, there's a way in electron production from the Q-square dependence where the gluonic, the hybrid baryons are supposed to have a zero longitudinal amplitude here. So that's a program for class in the future. And I think Victor will probably talk more about that in the afternoon. Okay, so where do experiments happen? Certainly data taken here at JLab, and then complementary to what's going on here at JLab, the measurements at ELSA in Germany and at Mainz. All these three labs are the dominant players at the moment, producing double polarization data for the proton and also for the neutron. Here at JLab, I'm going to show you more results from the G8 experiment, which had a linearly polarized TAC photon beam, and the Frost experiment is the double polarization experiment, where we used a butanol target. We took data with a longitudinally polarized target in 2007, 2008, and then 2 years later in 2010, early 2010, if I remember correctly, with a transversely polarized butanol target. Butanol is like a trash can, like having light incident on a trash can is really difficult to analyze. So to make our lives easier, we actually have 3 different targets in here: a butanol target, a carbon target, and a polyethylene target, to study the background that arises from the reactions of the butanol target. That is really helpful in our analysis. And that's a unique feature here of the Frost experiment that the other experiments in Germany don't have. So they need extra separate runs on carbon to study the background. Okay, for completeness also, what do we do with all the data? So at the end, we get polarization observables and cross-sections. That does not necessarily give us directly all the resonance parameters. So we need sort of like a machinery. So we need experimentally double polarization measurements. We need measurements of the neutron and on the proton, of the proton, to resolve the isospin contributions. And we need all of that for a large variety of channels to extract resonances. And then we're starting up here experimentally, so we need partial wave analysis machinery to find partial waves directly from the data, and then that has to go together with an approach from theory to extract the resonance properties then from this. So I'm just mentioning here, on the partial wave analysis side, the main players at the moment are the MAID group at Mainz mostly, the SAID group at George Washington, and then the Mongachina group, which is associated with the ELSA lab in Germany. And it's the Mongachina group that has mostly inspired the discovery of new resonances in recent years, and also changes in the PhD. I think they're at the forefront of doing this partial wave analysis at the moment for baryons. Okay, in a more naive picture, why are polarization observables important? What we want to do is determine the 4 complex amplitudes to describe single meson production here. And that requires, which has been worked out, 8 carefully chosen measurements, 4 double spin observables and 4 single spin observables. And what we have access to experimentally, we We don't have access to recoil polarization, at least not for the pseudoscalar reactions. We do have those for the Hypron channels, but not for like single fire, single layer production. And these are the observables that we can actually measure here. So 7 polarization observables plus the cross section that we have access to. What I'm showing here is the total cross section for Pi0 production, and these curves always refer to what I showed earlier here, to these partial wave analysis groups. And all of them can describe the pion cross section fairly well. However, we know that baryon resonances are broad and overlapping, so these solutions, when we look at like the helicity differences here separately for sigma 1/2 and sigma 3/2, then there's still these ambiguities that requires polarization observers to really nail down contributions to these solutions. Okay, from a more practical point of view. So that was for pion production, and since I'm showing this here, I can also show some recent results from ELSA that was published this year. So these are the angular distributions in the helicity difference for single pion production. And it was just nice to see that we got these results into physical review letters again, which has been a problem for spectroscopy for some years before when they changed the rules and made things a little bit stricter for us. But we're back in there, so this is exciting physics, and it's being recognized. Okay, so one other thing I wanted to show is so the helicity difference that I showed here. Here, that's this observable here for single pion production. So we have a longitudinally polarized target and a circularly polarized photon beam. Another observable that has been measured recently and published is the G observable, where we have still a longitudinally polarized target, but a linearly polarized photon beam. And I'm showing this here because not only do the labs work complementary in their efforts to produce experimental results, but also these groups put quite some effort into finding out what are the discrepancies in the partial wave analysis. So when we look at these curves here, there's still discrepancies, and it's also important to find out why do these groups and their solutions differ. So the discrepancies, for example, here in the pion channel have been traced down to these multipoles, which are connected to these resonances, and it's also quite important to find out why these solutions actually do not agree with each other. So there's quite a lot of effort, at least at lower energies at the moment, to also solve or resolve these puzzles. Okay, Pi0 production results from class that were published last year. So many of these observables are really coming together with unprecedented statistical quality. So this is the beam asymmetry in Pi0 production, and we're looking here at different production angles in the center of mass system versus energy, roughly from threshold to well above 2 GeV. The beam asymmetry in Pi0 production is not entirely new. For this reason, there's fairly good agreement between the theoretical approaches here and the data. However, we see that at higher energies in the 1900 2 GeV region, where we're mostly expecting the new resonances, there's still discrepancy, and these data will certainly help to improve the description and learn more about the behavior of these data. So this is the energy dependence for particular angles. You can also plot it in the different ways, the same data, but now plotted versus angle for fixed energies. And what we've learned from these data in particular, we see this sharp dip here at about 60 degrees in the center of mass angle of the pion. So a description of that in the later SAGE solution at least. We've improved the mapping of this dip near 60 degrees. And also some of the couplings have changed here to get a better description here of the data. So that's the beam asymmetry for Pi0. Here's the beam asymmetry in the same paper we published, the Pi plus production. Pi plus production beam asymmetry was not as well known as for Pi0. So you see here there are more discrepancies between the theoretical curves and the data. But these are also now, these data are now included also in these partial wave analysis and will improve the solutions. Okay, so now also another polarization observable is the helicity difference that comes from the frost run, the double polarization measurements. Again, he had fairly low energies, we see good agreement, but then at higher energies we see that like the structure of the data becomes more complicated, and that the description of the data also is depending on whether the data are included in the partial wave analysis or not. So to be fair here, I think the red line for the red line will say how the data were actually included in the partial wave analysis, whereas the other groups made mere predictions to these for these data. So, and of course the solution improves once the data are included. Okay, sticking with the same channel here, neutron pi plus, this is the target asymmetry. There has been quite some effort in the past already to determine the target asymmetry, so it goes back to the 70s. For that reason, it's also not a big surprise that we see quite good agreement here between the data and the partial wave analysis predictions or solutions. However, at higher energies still, well, not to learn we have here. So these are still early stage results from Frost D9E, where we had a transverse target polarization. And from the same data, we can also extract the F observable. And I know this is all confusing with all these polarization observables, even for us when we discuss that on a weekly basis. So the F observable would be longitudinal target, no, it's a transverse target polarization with a circularly polarized beam. This has not been measured before, and for that reason you see that there's still much more to learn from this data than from the observable that I showed you before. There's still reasonable agreement for W's below 1.7, but above we see the discrepancy. So all these data are coming together now, so we're pretty close, at least experimentally, to declare like huge success on the mission of complete experiments. Okay, just to give you a brief overview here, so I mostly showed the results on pi 0 and pi plus production. I think we're pretty close to putting all these observables together, at least without recoil polarization. For class, it's a little bit harder to work on eta and eta prime because they decay to photons, and the class detector is not very well suited for that. So the measurements at ELSA in Germany, they complement the efforts here at JLab. I'll show you a few more results on pi plus, pi minus production. There's also, I don't have time to go over all these reactions, but we have full machinery at various institutions for fine and mega production. And there are efforts with the HDI's targeted class to extract the similar observables for reactions of the neutron. And then a real complete experiment is possible in the hyperon channels. Cross sections have been measured before, and there will be a talk in the afternoon from Kay about these hyperon channels. Okay, for 2 pion situation is a little bit more complicated. I think the 2 pion reaction is really important because then we find intermediate states in these cascades, for example. But experimentally and theoretically, it's a real challenge to analyze these data. So before we had 7 polarization observables for single pion, that's going up to 15 observables now because we have 3 particles in the final state. And the 2 particles don't go back to back anymore, but we have like a pair of particles that form the decay plane, which forms an angle with the scattering plane, and that gives rise to more observables. But since the 2 pion cross section is the largest among above 1.8 GeV roughly, it's a really important challenge to be analyzed. Just to give you a flavor of the statistical quality, so 3 particle final state requires like 5 independent variables, happens in 5 dimensions. So this is the beam asymmetry. So we come in with a linearly polarized beam on an unpolarized target, and we are able, what I'm showing you here, is for a fixed energy bin, for a fixed angle in the center of mass system, we can essentially plot the observables for the 2 pions for the pi plus and the rest frame of the 2 pions. So this is in 4 dimensions. So to cut the long story short here, this is in 4 dimensions, and I'm proud to present the statistical quality for the observers. So there's a lot to learn from these data. We also, that was the GAB experiment from Frost. We can get the same observables from the double polarizations. Where we apply a complicated procedure to make the target unpolarized again. So what you see here is the blue points are what I showed you earlier, and the red points are from the double polarization measurements, and we see fair agreement, and that gives us quite some confidence also that we can handle in our analysis the butanol target properly. And the curve here, the red curve, is a fixed and narrow interval, and the data are not included, of course. Still not in there, yeah. Just to give you a flavor also, this is the ice circle, so unpolarized target and circularly polarized beam, where we can compare with previously data from the class here, the cyan data points as fair agreement, and it appears that we can even find a bin with the new data here. This is the target asymmetry, so unpolarized beam and longitudinally polarized target. So that appears to be flattening out at about 2 GeV. There's quite some rich structures at lower energies, but as you can see, the common approaches from the theory side are not very good. All these data that I've shown you are pretty much under collaboration review already. This is something that's coming together experimentally fairly soon. This is the helicity difference in 2-pion production. Again, these are under review, and we can release those to the theories fairly soon, where we also see rich structures here at lower energies, but it also appears to be flattening out at higher energies when more and more resonances can contribute to this channel. Okay, Eugene gave me 1 more minute. So we quickly summarize our understanding of baryon resonances. That's been greatly improved. So we see these additions to the particle data, to the listings of the particle data groups, so things are really happening and it's coming together. I don't think it's a little bit too early to really say like what is really the pattern of these resonances in the spectrum, but I think we're close to that. These are confirmed mostly these channels here, and glass has contributed significantly, in particular the strangeness channels here. But for higher resonances, there's no question that these double meson reactions are important, like 2-pion channels, pi eta, pi omega. And these analyses still have to continue in order to make progress. Okay, with that, I'll stop then.
Thank you. We have time for questions.
I'll shout. And this is probably a naive question. Of course, you want to identify the energy and the spin parity of these states,
right.
But to elucidate their structure, is there other information, couplings, and things that will help?
That is right. So, I mean, I haven't mentioned
and what can we get out from the polarization observables?
I haven't mentioned that explicitly, but the polarization measurements in photo production are mostly to map out the spectrum and to find signatures for new states. Then we have to go back to electroproduction and study the Q-square dependence of these states in order to really learn something about the structure of these states. So these are complementary efforts. I didn't really have time to do that. There was just one slide I had on the Roper resonance very early in the talk, but Victor will talk more about that in the afternoon. So these efforts go together, and the polarization observers are merely to really map out the spectrum and find states. Can't tell much really what the nature of these states is.
Any other questions? Okay, thanks all very much. We are moving to the next talk. The next talk will be fermion correlations from non-electron holes to mega-electron holes, covering a huge range.
Okay, so I want to talk to you about correlations from NEV to MEV. I'm going to start with a small advertisement for the Class Data Mining Initiative. Then I'm going to give an introduction to nucleon-nucleon correlations, some new information we've learned about NN correlations from the data mining, and then I'll talk about the connections to the NEV atomic correlations and TANS contact. So, Class Data Mining Initiative, what we wanted to do is we wanted to take all of the class nuclear target data, put it in one place with one common interface so that it's easy to access, and more importantly so that we don't just have access to the data, but we also have access to all of the standard class cuts and corrections, such as particle ID and so forth, that are necessary to actually make sense of the data. So these are all approved cuts and corrections that have been done because all of this data, aspects of which have already been published. And we wanted to make it easy to combine data from different data sets, SOA, service-oriented architecture, so that we can use lots of different processors at the same time. And then when this project was fairly mature, the DOE came out with their data management requirements, and we said, well, we do that. So we got a lot of people. Gagit Gavalian has done a wonderful job writing the software, and so we adopted the class software Clara for use in the data mining project, for talking to different, being able to download the data. If you want to download data, you don't actually have to compile anything. It's all written in Java, and it's really simple. There's an interface to root, so you can analyze the data that way. We have several data sets available on the ODU farms, and you can search it for whatever beam energy you want, whatever target you want, and so forth. And so you don't have to know that, gee, I want the carbon runs from E2, which were in June of whatever the heck year it was, etc. And then you can select whatever events you want to analyze. So we've got a whole bunch of analyses from a number of different institutions looking at this, generally looking at hard processes and nuclei. And the one I want to, that I'll be talking about later, the results are PP and PN short-range correlated comparison nuclei, paper on that we just submitted to Science last week. So, and I think the most important item here is the last one, which is, if you have any ideas, put your name here. So, what do we know about short-range correlations? Well, it's responsible for the high momentum part of the nuclear wave function. There were two very good talks from Bob Ringa and Higginbotham on Monday, and amazing calculations for A up to about 12. Using the phenomenological nucleon wave functions. And so it gives us the high momentum part, which is most of the kinetic energy, even though it's only about a quarter of the nucleons in heavy nuclei. But the momentum distribution at these large momenta is fairly similar for the different nuclei. So it tells us, we can learn a lot of things from it, including the short distance behavior of nuclei, possibly whether nucleons are modified in nuclei, and that's a connection to the EMC effect, which I will not talk about, and possibly extrapolating to cold dense nuclear matter, neutron stars. And I like to say that nucleons are like people. When they're at long distance, they ignore each other. When they're at moderate distances, they can interact, and when they get too close, they violently repel. So, what do we know about correlations? That this is momentum density against momentum in inverse Fermi, so 1 is 200 MeV over C, and at large momentum, the momentum density is almost entirely due to the correlations. But I mean, as an experimentalist, I need a signature for a correlation. What a correlation is I've got two nucleons that are fairly close distance, and they have a large relative momentum and a small center of mass momentum, which means that they're back-to-back in the nucleus. So with a mean field nucleon, its momentum is balanced by the other A-1 nucleons. With a nucleon in a correlated pair, its momentum is balanced by the other nucleon in the pair. So what we found is that correlations are universal. So here we have electron scattering from, cross-elastic electron scattering from a deuteron. You hit one nucleon, the other recoils with its initial momentum. And if you've got these if we've got these correlated pairs in the nucleus, they're scattering from one nucleon, the other one recoils with its initial momentum. The A-2 nucleus is a spectator, and the signal for that should be that when you look at the ratio of cross sections from nucleus A to deuterium, and here we have it for everything from helium-3 to gold, non-foaming state in Hall C, what we see is a plateau for x greater than about 1.5. And so for x less than 1.5, we're scattering from mean field nucleons, momentum distributions are different, the ratios vary. But for x between 1.5 and about 1.9, we're scattering from correlated pairs, and we see that because the cross-section ratio is flat with x. And the value of this ratio tells you the probability that a nucleon is in a correlated pair in this nucleus relative to deuterium. And since in deuterium, the probability that a nucleon has momentum greater than about 250 or 300 MeV/C is about 5%. We just take that and multiply 5% times this number, and that gets us the probability nucleon in a heavy nucleus is in a correlated pair, which is sort of 20–25%. Okay, so we know the correlations are there. Now we want to look at them, and this is some Paul A measurements, first done on carbon, q squared about 2Jeff squared, x again, slightly greater than 1, so in the quasi-elastic region, we're away from messy things like meson exchange currents and isobar configurations. We're looking at the missing momentum range of 300 to 600 MeV/C. The Fermi momentum for heavy nuclei is about 250, so this is nicely in the correlations region. Detect the scattered electron and the leading proton and the two high-resolution spectrometers, and then we look for the correlated partner, the neutron or the proton, in the big bite spectrometer and the neutron array behind it. And so the question is, what fraction of these knocked out high missing momentum protons had a correlated partner? And the answer is that basically all of them do. And that they're almost entirely, the correlated partner is almost entirely a neutron, and that it's about 5% proton-proton pairs. And so by inference we say, well, if it's 5% pp, then it should also be 5% neutron-neutron. But the point is two things. One, all high momentum protons have partners, and that they're NP pairs. So let's look in helium-4 and go to higher missing momentum. And so the open data points are the previous data on carbon, the closed data points are the new data on helium. And what we see is that proton-proton pairs are still a very small proportion of the correlated pairs, and it's slightly increasing, and we think we understand that. The proton-neutron pairs are still dominant, but they're decreasing from the 90% they were down to about 40% at the highest missing momentum. We still don't fully understand that. It could be 3 nucleon correlations, might be some other kinematic effects. So why do we have this incredible ratio of PN pairs to PP pairs? It's about 20. Well, it turns out that what we have is that in the range we're looking at, which is about 400 MeV/C, there's a minimum in the S-wave momentum distribution. The PP pairs have to be in an S state. The PN pairs can also be in a D state. So here we have the PP distributions from helium-3 to beryllium, and you see this minimum at about 400 MeV/C in the pair relative momentum. The PN pairs don't show that minimum because it's filled in by tensor correlations. Here we have the PP pairs in helium-4 that was just shown, the slide was just shown on Monday. I stole it from Bob's talk. And so at a total momentum of the pair of 0, you see this very pronounced minimum in the distribution at 400 MeV/C. This minimum slowly fills in as the total momentum of the pair increases from 0 to about 250 MeV/C. So we looked next in class, we looked at helium-3 EU prime PP, and we looked at the three-body electrodisintegration of helium-3, and it's fairly wide-ranging kinematics because it's class. We detect 2 protons, we identify the neutron by missing mass. It gives us a wide range in q squared and energy transfer. This red line here is x equals 1, so it's quasi-free kinematics. And we look at the energy distribution among the 3 nucleons, and we see 3 peaks in the Dalitz plot. So what I'm plotting is the kinetic energy of the first proton divided by the energy transfer versus the kinetic energy of the second one. Which one's the first and which is the second is random. And so we've got 2 peaks in these 2 corners outlined in red, where one proton has most of the kinetic energy, the other 2 nucleons each have up to 20% of it, and then 1 peak down here where the neutron has most of the kinetic energy and the 2 protons each have less than 20%. We've got a threshold for particles of about 300 MeV/C for detecting the protons. We put a similar threshold on the neutrons.
So all three particles have more than the Fermi momentum. When we do this, here we have the leading proton in a p-n pair. The opening angle of the p-n pair is very strong, is strongly back-to-back. When we restrict the perpendicular momentum of that leading proton, then it's almost entirely back-to-back. We don't see this in phase space. And so we're seeing something like this. Virtual photons coming in, hitting one proton. We're cutting on the perpendicular momentum to get rid of final state interactions. And then when we do that, the other two nucleons are back-to-back. And so it looks very much like they were in a correlated pair. And so what we can do is we can now look at both PP and PN, probability of PP and PN knockout. And so we look at relative momentum of the pair between 300 and 500 MeV/s. Here we've got the ratio of PP to PN. And so here are the Hall A and Brookhaven results at 0.05, the 20 to 1. But they're a relatively low total momentum of the pair. We can see this minimum filling in as the pair total momentum increases, and this dashed line here is just that counting of a half, because you've got one PP pair and two PN pairs in the nucleus. And it very nicely matches a Golok one-body calculation that includes the continuum rescattering of the correlated pair. And it's very much similar to Wernicke's calculation, where here you've got the minimum at 400 MeV/s at very small pair total momentum filling in as the pair total momentum increases. And so that's just a very strong, another strong signal that what we're seeing in these correlations are tensor correlations. So the next thing, so this was done on helium-3, helium-4, and carbon. And what we then want to do is extend this to heavy nuclei. This was a data mining analysis mostly by Orphan and Tel Aviv. And so we looked at targets from carbon to lead, and beam energy was 5 JeV. This was an ET2 data set. We put a cut on X greater than 1.2, and that basically gave us that Q squared was bigger than 1.5 JeV squared. We looked at missing momentum from 300 to 600 MeV/s, and required that leading proton was within 25 degrees of Q and carried away most of the momentum. And so that's what told us that we've got one nucleon, that's the one that was K. And so then we said, okay, how many of these protons have a proton partner? And so here we have the distribution of the detected proton with respect to the missing momentum. And so it's very correlated for all the nuclei. And so that tells us that that detected partner was in fact correlated with the leading nucleon. And we also looked at the angle between that recoil momentum and Q. And if it was due to final state interactions, we have a big peak right here. We don't. And so that tells us that final state interactions are quite small. And so then we can look at the ratios. And so what we have here, we're taking ratios to carbon in what we're doing. So it's sigma A, sigma for nucleus A divided by sigma carbon. Here we're going atomic mass, so here's carbon, here's lead out here. We've got 4 data points, carbon, aluminum, iron, and lead. And so this is the EE prime ratios, and we've got copper and gold instead of iron and lead for the EE prime. And then here we have our ratios E prime P and E prime PP. And they're smaller. We haven't corrected for rescattering of the outgoing proton because we know we're going to lose a lot of the outgoing protons because nuclei are not very transparent. But the thing to note here is that 2 proton knockout is not increasing faster than 1 proton knockout. And so what we expect is that if PP pairs were 5% in carbon, they're not going to be much bigger in heavy nuclei. We also look to see that our ratios are independent of missing momentum from 0.3 to 0.9, and they are independent. Here it is for aluminum, iron, and lead with respect to carbon. This is the ratio of EE prime P over EE prime PP. And so it's momentum independent, so the ratios mean something. And so then what we have to do is we have to correct for the nuclear transparency, and we do it with a Glauber calculation with potentials that match previously measured transparencies. We assume that all of the high missing momentum protons have a correlated partner. We don't see a whole lot of proton partners, And so we infer that, therefore, there are a whole lot of neutron partners. And we then calculate the actual fractions from this double ratio of EE prime P to EE prime PP for nucleus A relative to EE prime P to EE prime PP for nucleus carbon. And so we get that the PP fraction is sort of that same 5-ish% for all nuclei, and therefore the NP fraction is around 90%. So what does this tell us? Well, that the high momentum tail is still predominantly NP pairs. And so what we have is we've got an asymmetric system. Here we've got the majority. If it's just a non-interacting Fermi gas, we've got the dashed red line for the majority, the dashed blue line for the minority. The majority will have a higher momentum because there are more nucleons, and the radius of the majority is not that much bigger. But now we take equal numbers from the majority and the minority, and we put them in the high momentum tail. And that means that a given proton has a much higher probability to be in the tail than a given neutron. And so, if you've got a lot of boys and girls at a dance, and boys only dance with girls, and if there are fewer boys, then there's a greater probability that a boy will be dancing than that a girl will be dancing. So what this is important for the nuclear symmetry energy. And it could possibly explain the isospin dependence of the EMC effect, the Newteb anomaly, because after all, these are measured in iron. Iron is asymmetric. And so if there's a higher probability that a proton is moving fast, and the EMC effect is related to the virtuality of the nucleons, then you'll have a bigger EMC effect for the protons in heavy nuclei than for the neutrons. And these correlations are also important for understanding neutrino nucleus scattering, because some fraction of the time, when a neutrino scatters quasi-elastically from the nucleus, it's going to knock out two nucleons. So, what does this have to do with any of the correlations? Well, there's this quantity called TANS contact, and this is for externally confined Fermi gas, a two-component Fermi gas with a short-range interaction between the two components, and it's externally confined. And so what we need to have is that the scattering length, A, is much bigger than the fermion separation, D, is much bigger than the effective range of the potential. So it's basically a contact potential. And then, when you do that, what you get is you get a momentum distribution that drops off as k to the minus 4, where k is the momentum. And so what he does is he defines this C, this contact C, is just a limit as k goes to infinity of k to the 4th n of k. Okay, fine. What makes it interesting is that this C then describes an awful lot of the thermodynamical quantities associated with a system. And so what it gives you is a one-parameter description of what is a relatively complicated system. And so it can tell you about the energies, the short-distance correlators, the dependence of the energy on the inverse scattering length. This is something atomic physics people can change easily. Nuclear physicists have a harder time dialing the scattering length. Pressures and energy densities, and so it's very nicely worked out. And here's one example where they looked at TANS contact in a system with ultra-cold potassium atoms. So it's an optical dipole trap. They're at microkelvin temperatures, which gives you nano-electron volt energies. Two different spin states, and the scattering length between the unlike spin states is 800 times the Bohr radius. So here is a plot of k to the 4th times the momentum density versus k, where the momentum is in units of the Fermi momentum. And so starting at about 1.5 times the Fermi momentum, it's nice and flat. And so here's the value of C for this system. And here then is their measurement of the virial theorem, where they have the energy, the kinetic energy plus the interaction energy minus the potential energy. And the solid circles are the energy they measure directly. The open circles are the energies they should get just based on the contact, right here, plotted against this dimensionless strength of the interaction, 1 over the Fermi momentum times the scattering length. And you can see that they agree very nicely. And they can do things in atomic physics systems that we can only dream of in nuclear systems. So what does this have to do with nuclear physics? Because, well, we've got some problems. First off, it's not externally confined. It's internally confined. We have the advantage that we have unlike fermions, and the high momentum is dominated by unlike fermion pairs in the tail. But the end-to-end interaction is really complicated. The nucleus, as I said, is internally confined. And so we have to pick out one part of the nucleon-nucleon interaction and say, that's what gives us the unlike pairs. And so, well, we can say, here we go, if I look at just the tensor part, the scattering length is about 5.5 Fermis, the nucleon spacing is about 2 Fermis, the effective range comes from 2 pion exchange, so it gives you about 0.7 Fermis. Well, A is bigger than D is bigger than the effective length, but it's not much bigger. So does this work? Well, we look at the deuteron, and we plot k to the 4th n of k. The data points come from Werner Broglin's small a data. The solid line comes from an argon V18 potential calculation. And you can see that starting about 1.5 times the Fermi momentum, where the Fermi momentum we chose is not the Fermi momentum in deuterium, whatever that would mean, but it's a Fermi momentum for heavy nuclei. And so what we get is we get it's flat, and we get a contact parameter C that's about 0.6. Okay, well that's nice, but k to the 4th n of k is this complicated combination of d waves and s waves. You know, the s wave has this minimum around 400 MeV over c, and the d wave is here, and well, it's nice and flat there. So it's more complicated, but yeah, we've got some nice scaling, at least in this region. At much larger k, it's going to drop off. But what about heavy nuclei? Well, heavy nuclei, we know we've got TANS contact for deuterium. For heavy nuclei, we've got the ratio of heavy nuclei to deuterium that we measured by the ratio of electron scattering. And so what we get, we just take the ratio of the inclusive electron scattering cross sections that I showed you before, these A2s, and we multiply, we get TANS contact for a heavy nucleus by multiplying the thing we got for deuterium times A2, and we put it on this plot here. And so we've got here, the purple points are from the ultra-cold measurements of potassium. The blue points are measurements of similar things on lithium. And then we've got 3 red points for measurements on copper, carbon, and gold. And they fall on the same curve. So phenomenologically, it's looking like it's working. Theoretically, we still have to have some details to work out. So, what do we know? Well, we know from ratios of electron scattering that correlations are important in all nuclei. We know from ratios of 2 nucleon knockout that they're dominated by NP pairs in carbon and helium. And we have recently extended those measurements to heavy asymmetric nuclei, where they're still dominated by NP pairs. And so about 25% of medium to heavy nuclei are in short-range correlated pairs. It's about 90% tensor correlated. And we've got this neat connection to TANS contact that we need to work out a bit more, but it's very intriguing. So thank you very much.
Thank you. Questions?
When you were looking at the high A data, it seems like you inferred the NP correlations by not seeing the extra proton.
That's right.
Do you have, is that I mean, do you have to infer that, or can you just infer that there are no correlations in that set of data?
Well, we know there are correlations in that set of data from the EE prime ratios. So from the ratios of inclusive scattering, we know that in that range of proton initial momentum, that the nucleons are in correlated pairs. And so that's what gives us confidence in what is, as you pointed out, an argument for not seeing something.
Other questions? Anyone? So I have a question. You're looking at the NP and PP correlations question. At the beginning of the talk, you said, okay, so there's no reason to believe that spin correlation would be different from PP correlation.
That's right.
Can you tell more about that? Why that is true?
So in carbon and helium, we can just wave our hands and say isospin symmetry because they're symmetric nuclei. In lead, we can make the combinatoric argument that the neutron to proton ratio is 1.5, and so just by combinatorics, the probability of an NN pair is on the order of, say, twice the probability of a PP pair. Because it's 1.5 times as many neutrons, so 1.5 squared is 2. And we also know in carbon that NP pairs are about, so we measure PP pairs at 5% with pretty good precision. We measure NP pairs at 90% with, well, you can see the size of the uncertainty there. And so we know from carbon that NN pairs are small because there's not that much room left after NP pairs with the error bar, and so we just assume they're the same size as PP pairs. And then in lead, we figured they'd be about twice as much. This plot actually is just the NP fraction or the PP fraction for proton knockout. So we're completely ignoring NN pairs at this point.
Any other questions? All right, let's take speakers. Afternoon session begins at 1:30, and now there is a lunch for the students and postdocs at 1:30.
Pardon?
about pi minus pi plus ratios.
Okay, so I'd like to thank the organizers for the invitation to present our results, which were just published a few weeks ago in this physical review letter. So the work that I'll be presenting has been done. A lot of people for the Applied Form Factor Collaboration have contributed. I particularly want, whoops, what did I just do? There we go. Okay, sorry. I particularly want to thank Cornel Buticiano, Hank Block, Dave Gaskell, Dave Mack, and Tanya Horn for their contribution. Okay, so of course a lot of people have talked about generalized parton distributions, so I certainly don't have to say very much. So again, just wanted to briefly summarize that, of course, the extraction of information in the generalized parton distributions depends on factorization of the hard scattering from the soft physics encoded in the generalized parton distributions. Particularly famous are the 4 GPDs of leading twist, the unpolarized HV and the polarized H tilde and E tilde. But over the last few years, what has been particularly people made aware of is the importance of the second set of 4 GPDs at twist 3, HT, ET, etc. In particular, I want to single out here HT, which in the forward limit reduces to the transversity distribution, which of course is critical for understanding of the proton spin structure. Now, the dominant twisting contribution from HT contributes to the pseudoscalar amplitude, and so therefore, of course, pine production processes are going to be extremely important for understanding that. And it's the contribution of HT is manifested in the transverse cross sections, the interference terms, as well as, of course, various types of single spin asymmetries. Now here, in particular, I'm going to talk about deep exclusive pine production, where the electron is scattered in this cartoon, creates a single pi plus going at forward direction off of the proton target, or if instead we could substitute a neutron target here, then you would produce a single pi minus. Now in particular, what we want to do is to form ratios of pi plus production on the proton compared to pi minus production on the neutron. And if we can do this, then maybe, if we're lucky, there will be some partial cancellation of non-perturbative corrections, and this would then lead to some early insight on the factorization of the hard and soft physics at intermediate Q squared. So for example, there's a prediction by Nachman made roughly 40 years ago, which is that if we look at using transversely polarized virtual photons on the neutron, creating a single pi minus, compared to the same process for a pi plus on a proton, that ratio, which we call RT, and then if we go to sufficiently high values of form momentum transfer T, then the virtual photon couples directly to the charges of the relevant quarks, and this ratio should converge to a value of about 1/4. But of course, the issue as usual is what is sufficiently high T in order to do that. Now, in addition to this motivation for understanding RT, there's also another one, which again is related to the chiral odd transverse GPDs I just briefly mentioned, that RT is not complicated by the pi and pole term, and so it would be a possibility for being especially sensitive to HT. Okay, now if we go to the opposite kinematic limit at very low T, then in that case the virtual photon does not couple to the struct quarks, but instead we have mesonucleon degrees of freedom. Now, in particular, for the Pine form factor experiment, we're interested in this T-channel diagram here, where to extract the Pine form factor, the virtual photon must couple to a virtual pion in the Pine cloud of the proton, knocking it on shell at high momentum and forward direction. Now, this T-channel diagram, due to G parity conservation arguments, is a purely isovector process. And so, if one does the isospin decomposition and now forms the ratio RL, where this photon is now longitudinally polarized, then the pi minus to pi plus ratio is sensitive to the difference of the isovector minus isoscalar amplitudes divided by the sum. So if this ratio differs far from 1, then that would indicate a significant presence of isoscalar backgrounds, such as, for example, here having the B11235 as an example. And this, of course, is very relevant for the extraction of the pi form factor from this diagram in pi electroproduction, which is why we were approved the meantime to take this measurement. Now, before our measurement, the only available, this is the entire world data set above the resonance region prior to our experiment. These data were taken at DESI, the fixed target station, in the 1970s. They are completely unseparated. There's only partial azimuthal coverage, and so they could not do an LT separation. But what they find is quite intriguing. This is versus T here. So at high T, intriguingly, the pi minus to pi plus ratio converges to roughly a quarter, which is consistent with Malcolm's quark scaling ratio, while at low T, it, of course, is fairly close to 1, which is what we would expect from pi and pole dominance. But again, these are unseparated cross-sections. To really do anything definitive, one has to do a Rosenblum separation. And so this is the relevant cartoon many of you are familiar with for Rosenblum separation, where we need to basically take 2 experiments where we vary the beam energy in this manner in order to adjust the virtual photon polarization while keeping the Lorentz invariant quantities q squared, w, and t constant. Now, if we can do the measurement at very small t, so that this takes the minimum kinematically allowed value, then the longitudinal cross-section has the maximum contribution from the pi and pole, which is of course relevant for measuring the pi form factor. Now, we need to investigate the t dependence at relatively fixed q squared and w. But the problem is that q squared w, t, and this angle theta, the angle of the pi from the q vector, that only 3 of those 4 variables are independent. And so in order to vary t then, while keeping q squared and w constant, we need to vary this angle. Once we start varying this angle, that means that now this reaction plane doesn't have to be the same as that one, and that means we actually have to measure the full azimuthal coverage in order to disentangle the 2 interference terms from L and T. Okay, so these data were taken in JLab Pol C using the 2 spectrometers, the HMS, which is a forward angle detecting the high momentum pion, and then the SOH, which of course has been now removed from the hull, was used to detect the lower momentum scattered electron at larger angle. So the data were taken in 2 different experiments, FPI1, which was taken really a long time ago, 1997, where the beam energy was a maximum of only up to 4 GeV from the LINAC at that time, giving us q squared at 0.6 to 1.6. And then in 2003, with higher beam energy being available, we were able to take, in this case, 1 additional measurement on the pi minus pi plus on deuterium at a q squared of 2.4 and at a higher W above the resonance region. Okay, so we're trying to select then using a deuterium target either a single positive or negative pion. This is our event selection where after we do the particle identification for a pion in the HMS and a scattered electron in the SOS, we have very clean coincidence time spectrum. This is a logarithmic scale. And then after doing that, this then shows our missing mass reconstruction here, which is a spectator nucleon plus, of course, the other recoil nucleon. So this is reconstructed assuming in the quasi-free approximation. Double pi production would be out in this region, so it's very cleanly excluded. And then these are the diamond cuts here, which are q squared versus w, which are applied in order to equalize the acceptance at high and low epsilon in order to do the LT separation. Now, that all sounds very straightforward, and of course we're experienced with that, but the thing that was really the complication in this data analysis was the following. That when you detect the pi minus, the pi in arm, its magnetic field has to be, of course, set for negative polarity as opposed to positive polarity for the pi pluses, so they're not, of course, detected simultaneously. Now, there's a huge, enormous asymmetry in the background when we detect the pi minus compared to the pi plus, because all of the scattered electron background goes up the pi spectrometer when we do the pi minus runs, but of course that background does not go up the spectrometer whatsoever for the pi plus runs. So that is sort of illustrated here, where I have the different colors, don't worry so much about it, the different kinematic settings. This is for the fpi1, all of the pi plus data runs, where I'm showing the rate in the pi and arm, the HMS, versus beam current, and we were able to successfully keep the rates down to 500 kilohertz or less, which is where we have reliable tracking. But for the pi minus runs, this was something that we didn't fully appreciate before we started taking the data, was just absolutely how enormous that electron background would be. And even though we really lowered the beam current down a lot, even still, we had maximum rates up to 1.4 megahertz in the HMS. So we had to do a lot of work to really understand that. And of course, for the second pi form factor experiment, we were much more aware of this problem and took great pains to avoid this. But we needed to understand this in order for the fpi1 data. So I'll just briefly enumerate some of the things that we had to do. So fpi1, as I said, ran in 97. fpi2 ran in 2003. There were a huge number of changes in between, both hardware as well as, of course, software improvements. So one of the things that had been greatly improved between the two experiments was the HMS tracking software, where it was able to do a much better job of selecting the best track if there are multi-track events. And this, of course, is particularly important for those pi minus runs at really high rates. So we had to do a lot of work, actually, to modify the Halsey analysis engine in order to accept the older format data from fpi1, because even the data format had changed. So here to sort of illustrate the importance of this, so here shown with the black points is the first replay of this fpi1 data back amazingly long ago in 1998. And these efficiencies all look very nice, but actually they're overestimated. Again, the old tracking code does not handle 2-track events so well as 1-track events, so a lot of them are excluded. And so the efficiencies are overestimated since 2-track events actually have lower track efficiency than 1-track events. So then, after making the adjustments to the engine, we did a second replay using the 2003 version of the engine. The tracking efficiencies are lower, but they're still overestimated. So for the second pi form factor experiment, what we did, now for the second pi form factor experiment, the data are way down in this region here. Again, this plot is for fpi1. But what we found is that for the second pi form factor experiment is we didn't modify the tracking algorithm at all, but the algorithm to calculate the tracking efficiencies was modified just slightly, that the cut to exclude multiple good PMT ADC signals within the fiducial region of the otoscope was removed. And that resulted in slightly lower, actually more accurate tracking efficiencies. But the problem is once we go to these very high rates for the pi minus data, as you see, that removal just really doesn't work at all. So finally what we decided to do was to take the 2003 tracking efficiencies, but then apply a correction factor. So now, of course, you're wondering, well, how did we determine what that correction factor was? Okay, so in order to do that, one of the things that we did in the second pi form factor experiment is we did a large number of what are called carbon boiling studies. Of course, carbon, unlike cryotarget, should not boil. And so if we take a series of runs where the only thing we vary is the beam current, and so therefore, of course, the rate in the HMS, that if all our efficiencies work out correctly, then our normalized yield should be independent of rate. Well, as you see here, it is not. And the reason why it is not is, again, because the tracking efficiencies are overestimated at high rates. So this slope, roughly 6% per megahertz, tells us by how much we have to adjust the tracking efficiencies by. So that is how we determine that correction. Once we do that, then we can go ahead and look at our cryo-target boiling studies in great detail. And again, there were large numbers of hardware improvements between the two experiments. In FPI-1, the older experiment, the cryo-target was with the beer can geometry, which is like you take a beer can and the beam goes down the axis. And also the beam raster was had a very non-uniform profile. It was square, but the beam spent most of its time actually in the corners looking like bedposts. So that, for that, we had a cryo-target boiling correction that we needed to apply of this amount. And this is particularly important actually for the pi plus runs, because for the pi plus runs, we're able to take them at higher beam current than the pi minus ones. For FPI2, there's superior geometry of the cryo-targets, the so-called tuna can, where you take a can and you shoot across the diameter of the cell, and the beam raster was dramatically different, and for that we find that no correction is needed whatsoever. So then finally, the last major correction, and this is the one that caused us by far the most anguish, was the HMS Cherenkov blocking correction. So again, because of these very high electron rates in the HMS, and of course we knew we would have electrons in advance, just maybe didn't appreciate quite to what magnitude, the HMS gas Cherenkov was a veto in the trigger for the pi minus runs. I mean, if we had it in the trigger at the pi plus runs, it wouldn't trigger anything, and so it has no consequence for the pi plus runs at all. So in order to avoid high dead time, this Cherenkov needed to be in the trigger. The issue is that if we have two particles within the resolving time of the electronics, so imagine we have a pi minus going through the gas Cherenkov, but then within 100 nanoseconds of that, an electron also goes through the gas Cherenkov. That will cause then a veto of that event, and so we need to be able to identify and correct for that. So we did a fairly large number of detailed studies, which I will not go through. I'll just simply give our final result, is that we finally obtained the Cherenkov blocking correction from the trigger TDC information. This one we believe to be the most reliable because it's independent of all of the other tracking efficiency and cryo-target corrections. So here we have this is a multi-hit TDC, so for a single event we can have multiple hits, and for these runs shown here, the Cherenkov veto is not enabled. So this is a TDC of what the Cherenkov veto would have done if it was implemented. And so this peak here would then correspond to valid vetoed events. These would correspond to electrons being vetoed. And then what we have here is this is the region after that where a second hit happened on the Cherenkov. This area before is taking into account in other corrections due to early electrons passing through, and you don't have to. But this width in nanoseconds, then that gives us then the effective gate width in this blocking correction. So finally, after applying all those corrections, we can have reliable yields, and the response functions can be determined in an iterative procedure. So we improve the azimuthal coverage compared to the DESI measurements by taking multiple HMS. Okay. So I need to really run. Okay, so we took multiple HMS angles. Then we formed the ratio of the experiment to the Monte Carlo. And then from that, we extract then our unseparated cross-sections, do a fit, and then extract before separated functions. Okay, so I really have to run. I just got my thing here. So I just want to mention here that in our systematic uncertainties, that the uncertainties are larger for the pi minus than the pi plus due to the tracking correction and the veto correction, but they're all fairly well understood. One of the issues that we have is that the pi minus runs we were not able to take all of the settings compared to the pi plus, so that affects the T range of the data. So here we have the T range of our data here. So these are the separated cross sections. The pi and pole is approximately over here, and so the longitudinal cross sections go up very steeply. Here's for pi plus, this is for pi minus. The transverse cross sections are much flatter. Okay, I'll skip that one. Here we have we form ratios of the transverse to the for pi minus, and here longitudinal. So here we see that our results follow nearly a universal curve. The open squares are photo production results from SLAC from the 1960s for comparison. And what we find intriguingly is that we go up in T, up to a T of roughly about 0.35 or 0.4, is that the ratio comes quite close to 1/4. And so the open question is this an indication of Knox-Ewens quark charge scaling ratio? This seems an awfully low value to apply. Maybe indeed there is some partial cancellation of soft QCD corrections for it. For the longitudinal ratio, there's no universal curve at all, or neither is one expected. But we find that as we go to the minimum T value for each kinematic setting, is that the ratio comes fairly close to 0.8. And that is actually a value which was predicted by Frankfurt et al. In their large number of colors limit calculation in 2000. Now, for the relevance for the pi and form factor extraction, what we find is that these are then various predictions by Reggie plus other models. And we see that at larger T, that the ratio deviates, of course, from 0.8 for the F pi 1 data, but not so for the F pi 2 data. And this is qualitatively in agreement with our experiments, where we found evidence of a small additional contribution in the longitudinal channel, not taken into account by the VGL model, but we did not find any evidence of that contribution in F pi 2. Okay, here I have a comparison with the Golov-Skokov-Kroll GPD model, which is shown here in red. You can see that their calculation does quite well at the higher Q squared, and even for sigma T, their calculation is doing reasonably well. Again, for the sigma T here, there's substantial contributions from the HT twist 3 GPD. However, I should point out that the parameters are optimized for very different kinematics than ours, very small skewness and much higher W. So one should not look at this more than just that the ratio model is doing reasonably good for this. So one would then be quite hopeful that if one had a model which is actually optimized for JLab kinematics, that maybe one could be sensitive to this GPD. Okay, so the only other thing to mention is that for the longitudinal transverse ratios, that in pi plus is in black, pi minus is in red, and our other hydrogen results are shown in green, which maybe doesn't show so well on this screen, is that as we go up in Q squared, you can see that these ratios drop, but the ratio does not drop as quickly for pi minus as it does for pi plus, and so the LT ratio becomes more favorable for pi minus as Q squared increases. I already talked a little bit, of course, about Knox-Ewens quark charge scaling ratio and how our results are intriguingly consistent with that at the higher T. Another indication of that mechanism is that sigma TT over sigma T should also be suppressed due to his S-channel histidine conservation. What we find is that's this ratio here. As we go up in Q squared, you see this ratio drops in magnitude quite considerably, gets quite close to 0. And so that means that sigma tt is falling much faster with q squared than sigma t. So that's qualitatively consistent with that as well. Okay, so we do plan to take some more deuterium data in the approved F/12 Pine form factor experiment. So these are projected data of what we anticipate it might look like in comparison with the Branks-Rickebusch model as an example. And so what we would expect is, of course, we want to again confirm that the Pine form factor measurements are not plagued by isoscalar backgrounds, but also we want, of course, we would be able to see whether the data also converge again to 1/4 at a higher q squared and similar x. So if this is the case, then the hypothesis of quark knockout would be strengthened further. Okay, so we're, I think, out of time, so I'll just leave my summary here. Okay.
Does anyone have questions?
I think what you are extracting, this ratio by minus or by plus, very complex object.
Yeah.
Even if I forget about any complication of deuteron diagram, it's impossible to expect just T-channel processes. At least current conservation require additional diagram. Therefore, my question is, if I compare, even at this point, experimental data and model, they are so different that perhaps we very far from understanding of this ratio dynamic. And the question is what you are going to do in order to extract from the data the physics you are mentioning about scaling and so on. What analysis approach you should apply?
Okay, well, thanks for the question. So, of course, these models are not done on deuterium directly. The pi plus model is done on the proton, free proton, and the pi minus is done with free neutron. And as you say, this is a deuterium target and there are other issues. Now, one would certainly hope that some of these issues will cancel in the ratio, but you're correct, there's no guarantee. So hopefully now that our data have been published, this will motivate some specific calculations for this reaction. I mean, we're not going to change the extraction of the cross sections. I think it's really theoretical work that is needed to do a proper calculation on deuterium. So we've already been in discussion with some theorists who are very intrigued with our data.
Any other questions? Okay, let us thank Garth again. Okay, so our next talk is by Jasuni, and she will be talking about TPE.
Thank you. Thank you very much for inviting me to talk here. So I'm going to, as you can see, I'm going to talk about the class 2 photon exchange experiment today. And in my talk, I'm going to tell you why we did it, how we did it, and what did we learn from the experiment. And let me start my talk with the well-known proton form factor puzzle. The proton form factors GE and GM, they describe the proton charge and magnetization distribution. And there are two methods to measure these quantities. One is called the Rosenbusch separation method, and other one is called the polarization transfer method. And this figure shows the GE to GM ratios obtained from those two methods as a function of q squared. As you can see, up to 1 Jeff squared, the two methods seems agree with each other, but then there's a big discrepancy between the two methods. And as you can see, the discrepancy increases with the q squared. So in order to understand the structure of the proton precisely, it is important to resolve this puzzle. And one possible explanation is the two-photon exchange corrections to the Rosenwood separation measurements. Let's see what are the possible two-photon exchange effect on the Rosenwood measurements. So in 2003, Gulshan and Vanderhagen, they developed some formulas to include the two-photon exchange correction to the cross sections. So if you consider only the one-photon exchange, the cross section is proportional to the form factors like this, as in this formula. And if you have the two-photon correction, now the proton form factors are going to be modified, and there will be another additional term, which is it's an epsilon-dependent term, and this Y2 gamma is the two-photon exchange amplitude. And this, if you have the two-photon exchange correction, you have this additional term. And let's see the process in the diagram. So this is the reduced cross-section as a function of epsilon. In the Rosenwood method, what they do is they measure the reduced cross-section as a function of epsilon, and they extract the G and GM from the slope and the intercept. So these blue data points are the original Rosenwood measurements obtained at q squared equal to 0.64, and this red line here is the slope predicted by the polarization transfer measurements. As you can see, there's a few % difference in the cross section, but there's a large impact on the slope of the curve, or there's a large impact on the GE extraction from the Rosenwood method. So before I talk about the TP measurement obtained from the cluster photon exchange experiment, let me take a few minutes to talk about the TP calculation. So these are the Feynman diagrams describe the two photon exchange process. So we have a cross box diagram and the box diagram. And so first we have a one photon exchange from the lepton to the proton, and then there's this intermediate state, and there's another photon exchange from the lepton to the proton. So it's hard to do it's hard to calculate this TP correction, because if you want to do that, you have to integrate over all possible intermediate proton states. However, some people and groups, they try to calculate these two-photon exchange correction both in hadronic framework and the partonic framework. And what I have here is the TP calculation obtained in the hadronic framework. In 2005, Blunt and Melichok and John, they calculated the TP correction considering only the proton intermediate state, and this is what they found. So this is the TP correction as a function of epsilon, and for different q squared values. As you can see, the two-photon exchange correction is more significant at high q squared and low epsilon. So even at q squared equal 1, there's a significant amount of two-photon exchange correction. And then they applied their correction on the Rosenwood separation method. And this is with no TP correction, and this is with TP correction. As you can see, the TP correction reconciled the two methods up to 2 to 3 Jeff squared maybe. So anyway, here we're going to talk about the two-photon exchange measurements. So how we are going to measure the two-photon exchange correction? In this diagram, you see all the processes involved with the lepton-proton elastic scattering cross section. We have a Bode approximation term, and then we have these first order corrections. And actually these first order corrections are already included on those polarization measurements and the Rosenthal separation measurement I showed you. So then the next most uncertainty should come from the two-photon exchange processes. So we can write down the cross section as the square of the summation of all these amplitudes, and we can expand it, the equation as this. So one thing to note here is that the sign of this interference term between the Bode and the two-photon exchange is proportional to the charge of the lepton. So now if you get the ratio of positron-proton to electron-proton cross-section, you can easily determine the two-photon exchange correction. So in class two-photon exchange experiment, what we are going to measure this positron-proton, electron-proton scattering cross-section using mixed electron-positron simultaneous electron-positron beam. This is how we produce a mixed electron-positron beam at OP. We have a primary electron beam coming from the accelerator. It is 5.5 joules with ranging from 100 to 120 nanoamperes. The beam first passes through a radiator. At the radiator, some of the electrons radiate high energy photons. Then we keep the photon beams while throwing out the remaining electrons to the Tagger down. The photon beams pass through a converter. At the converter, some of the photons convert into positron and electron pairs. And then we use this special magnet, we call it chicane, and it's actually 3 dipole magnets, to separate the lepton beams, stop the photon beams, and recombine the beams again. The combined positron electron beam interact with the target. Target is a 30 centimeter long liquid hydrogen target, and we detect scattered leptons and protons from the class detected. So in addition to these main components in the beam line, we also had a lot of shielding to avoid the unwanted particles hit on the class detector, and we also had this PP calculator to measure the incident positron and electron beams separately. And more about the experiment. So we record all events that have a hit on forward calorimeter and opposite time of flight counters. So as you know, the class is nearly 4-5 detectors, so we detect scattered particles over a wide range. And in order to match the acceptance, we make sure to select the regions that have 100% acceptance for both positron and electrons. To control the systematic, we make sure to reverse the torus magnet field and the chicane magnet field periodically, and that's going to cancel out the artificial charge asymmetries. And finally, we use 4 kinematic cuts to select the elastic events for the measurements. And here's the kinematic coverage of our data. This is just for one configuration. These are the positron-proton events with positive torus polarity. And as you can see, it has a continuous wide Q² epsilon coverage, and we have a lack of data here due to our trigger. And I have also shown the beaming schemes for the high Q² data and high epsilon data in this figure. We are going to talk about these 2 beaming schemes in the next 2 slides in details. So before we go to that, let me talk about the ratios. So we calculate the ratios in 3 steps. So we first calculate the ratios, calculate the single ratios. It's just the number of positron proton elastic events divided by the number of electron proton elastic events, and for given class torus magnet field. And we assume that the proton acceptance are cancelled out at this point. And then we flip the torus polarity and we combine the single ratios and calculate the double ratios for each chicane polarity. And again, we are assuming the lepton. So, and we also have seen some background at low epsilon mean, so we make sure to remove those background. We also make sure to remove other events that has a hit on dead detectors of class. And this is the quadruple ratios. As a function of epsilon, you obtain for these 5 beams. So the black points are without radiative corrections, and red data points are after we correct for the radiative correction, radiative effects. So as you can see, we clearly see an epsilon dependence at this Q-squared value, and as we predicted from the theory. And these are the results at epsilon 0.88. So we are trying to check whether there's any Q-squared dependence at this epsilon value. Again, background subtracted, the detector corrections are applied. So again, this is quadruple ratio as a function of Q-squared. And but according to our results, we don't see any strong Q-squared dependence at this epsilon value. So now let me talk about the sources of systematic uncertainties. The major contributions of systematics are coming from the positron-electron beam luminosity differences and the class detecting imperfections. And we try to estimate those contributions using beam, chicane, cycle variance, and the sector variance. So I'm going to talk about this positron-electron beam luminosity difference in detail in the next few slides. And in addition to that, there's some contribution from the background fitting, the elastic event selection, and background subtraction, fiducial cuts, and target vertex cuts. So systematics due to the positron-electron luminosity differences. This is a part of our beam line. This is where we create the E plus E minus pairs. And so the pair production is inherently charge symmetric, so we should expect to see the similar incident beam, incident energy distribution for electrons and positrons. Since we are using a tertiary beam in our experiment, and we didn't measure the incident beam energy during our experiment run, but we could reconstruct the beam energy distribution with measured quantities like momentous and scattering angles. And this is the reconstructed beam energy distribution for electrons and positrons with positive chicane polarity. So even though we expect to see the similar distributions, they're slightly off. But the thing is, when we reverse the chicane polarity, now we're getting the same distribution, but for the reverse polarity of the lepton. For example, incident beam energy for the positron here is equal to the incident beam energy for the electron here. So what this tells us is that the beam transportation through our chicane is not perfectly symmetric. We have also some measurements from two-photon TP calorimeter, and using those measurements, what we did is we look at the positron coming from the left side of the chicane, and we compare that with the electrons coming from the left side of the chicane, and now we get the ratio equal to 1. And we did the same thing for the right-hand side of the chicane, and we're going to get we got the same similar ratios. But unfortunately, the answer does we we didn't have much TB calorimeter data, so the uncertainties are not so great. So anyway, the chicane is not perfectly symmetric, but the positron coming from the left side is same as the electrons coming from the left side of the chicane. So what this tells us is, by periodically flipping the chicane, we can get the symmetric luminosities. And if there's any remaining luminosities from the positron electron luminosity difference of the positron and electrons, we are going to measure that with by comparison of magnetic cycles. So I told you that we reverse the chicane and porous polarities periodically during our experiment run. So that gives us 4 magnetic cycles. So these are the double ratios we obtain for the positive chicane. These are for the 5 high Q-squared beams, and for those 4 cycles. As you can see, we are going, the ratios are almost similar for all cycles. And what it tells us is our chicane is reproducible. Chicane is reproducible. So, and then what we did is we measured the variance of these ratios at for each beam, and that ratio includes both statistical and the systematic uncertainty. So in order to isolate the systematic uncertainties due to the luminosity differences, we subtract the statistical uncertainty from this total variance. That's how we estimate the systematic uncertainties due to the luminosity differences. We use the same method to 6 class sectors to determine the systematic uncertainties due to dead detectors. So now let me show our results with the system, including the systematic uncertainty. So these red data points are the class preliminary data points, and the inner error bars gives you the statistical uncertainties, and the outer error bars gives you the total uncertainty, which is the statistical plus systematics. And this black data point here is the preliminary data obtained from the recent experiment, Web3 enormous experiment. And the blue curve is from the London calculation. And as you can see, our results agree both with the Novosibirsk results and the London calculation. Our uncertainties are not so great as the Novosibirsk, but we have large epsilon coverage than the Novosibirsk experiment. So they have just 1 data point. And then we also did some. We also did a small study to see how our GP correction applied on the available Rosenbluth measurements, and how the GP corrected Rosenbluth measurements agree with the polarization measurements. So these are the G to GM ratios as a function of Q squared, for Q squared 1 to 2 GM squared. And when I zoomed this area, I found these 2 data points. This is the Rosenbluth separation measurements obtained from Adivahis at Q squared equal 1.75, and this is polarization measurement obtained from Panchabi at 1.77. And what we are going to do is, I'm going to apply a correction on these and going to compare with this data point here. So these are our preliminary results. So this is how the correction is going to apply on the cross section. So we calculate R. So we can, from the feed, we can get the R, and then we can get the 2-photon exchange correction from this formula. And then we're going to apply that correction on the cross-section as seen in this formula. And this is a reduced cross-section as a function of epsilon. These black data points are the original data from antibodies and the group. And the blue data points are the TP-corrected Rosenbluth measurements. And as you can see, the TP corrections has a large impact on slope. It's about now, it's changed by about 20%, but there's no much impact on the intercept. And then I convert that into the converted form of G to GM ratios, and now this is the original data point, and this is the TP corrected data point, Rosenbluth measurement, and this is the polarization one. As you can see, the TP corrected one results measurement agree with the polarization constant measurement, but now we are getting the large uncertainties due to the uncertainty coming from two foreign exchange correction. And finally, the summary of my talk. The class TP experiment measured cross-section ratios of a wide range of Q squared and epsilon. Our results agree with the Hadronic calculation, which reconcile the form factors up to 2 to 3 Jeff squared. And TP corrected, and I showed you that the TP corrected Rosenbluth ratio agrees with the polarization at Q squared equal 1.77. And so it seems like the proton form factor puzzle is good to solve up to Q squared equal to 2 Jeff squared. But we will definitely need more data at Q squared larger than 2 Jeff squared, where we see the large discrepancies. So, that's what I have to tell you today. So if you have any questions, I'm happy to answer.
Is there any questions?
Oh, two very simple questions. Is that all the statistics you have for this data point? And the other question is, do you have any higher Q squared value there?
No, this is the highest Q squared data point we have, and this is all our
This is the highest. That's all the statistics. Thank you.
Any other questions? Okay.
Probably I can say it. Right? So what about the radiative corrections? So did you apply radiative correction and how big they are?
The radiative, okay. So the results I showed you is include radiative corrections, and it's the size of the radiative corrections are about the size of two photon exchange correction, and we actually a radiative correction as the interference term between the proton Bremsstrahlung and electron Bremsstrahlung term, which is the only significant charge or term appears on the ratios.
Still have time for another question? Anyone? Okay. Well, let us thank Sani again then. So up next is Kay, who will be talking about the Lambda 1405.
Okay, so I would like to thank the organizers for inviting me to give this talk. The talk I'm going to give today is about the Lambda 1405 hyperon and what we have learned from a string of papers that class has published recently. So this is the outline of my talk. In the first part of my talk, I will talk about hadronic spectroscopy and how we want to understand the lambda 1405 in that context. In the second part of my talk, I will talk about some of the class results that have been published in the past year or so. So the main result was the line shape of lambda 1405. That was the main interest. But we have also published results on the photoprojection cross-section for the lambda 1405 and also two nearby states. The third result that we have is a direct experimental spin parity measurement, and this was also a very recent result. I'll talk about that. And at the end, I'll talk about some prospects and conclusions for the future. So the first part of my talk is about hadronic spectroscopy and the lambda 1405. So in hadronic spectroscopy, the broad goal is to understand the spectrum of the hadronic states that we observe in experiment. So what are the underlying QCD degrees of freedom, and how do they manifest themselves as the states that we observe in experiment? So one of the goals of this would be to try to match up the experimental spectrum that we see with any kind of calculation that is based on QCD. A different aspect of hadronic spectroscopy is, can we identify states that have some interesting features? This could be, for example, some kind of state that doesn't seem to belong in the spectrum, or is suspected to have some kind of internal excitation or something that you don't expect for other states. So we want to study these states, and we want to know, okay, so what do these states tell us about the underlying QCD dynamics? So what is the lambda 1405? The lambda 1405 is a 4-star state in the PDT. That means that we think that we know this state very well. Nobody doubts its existence, and it is the first excited lambda state. So the lambda states are, of course, the baryons with 1 unit of strangeness in them, and the lambda 1405 is the first excited state. So the PDG puts the mass and width of this particle as about these values, but later on I will talk about how these numbers are a little bit suspect with regards to the new data that we have accumulated. So if you plot the spectrum of the lambda states here as a function of their mass, you start out with the ground state lambda, and lambda 1405 is this state here, the first excited state. So there is this NK bar threshold. So if the mass of the state is above this threshold, then it can decay into NK bar, but below that it cannot. So this lambda 1405 is right at this threshold, and there's higher states like the lambda 1520, and so on that go on beyond. So one of the interesting things about the lambda 1405 is that the consistent work model, which has had a lot of success in predicting the masses of a lot of the low-lying, low-mass states, it actually has some difficulty in predicting what the mass of the 1405 should be. So I just talked a little bit about the NK bar threshold. So why is that important? It's important because a lot of the experiments in the past have seen this peculiar line shape for the lambda 1405. So what does that mean? That means that if you do an experiment where you produce lambda 1405, then this thing will decay into a sigma pi final state. And the interesting thing is that if you plot the cross section of the 1405 as a function of this invariant mass of sigma pi, then what you're going to see is you're going to see this very sharp rise from threshold. So up, oops, sorry, and you hit a peak at about 1405. That's where the name comes from. But then you see this rapid drop off as you approach the NK bar threshold. So that means that this state probably has a very strong coupling to this NK bar final state, although it is nominally below that threshold. So this seems to be very interesting, and it also affects, so what is the interplay between the sigma pi final state that this thing is decaying into and the NK bar state that it is very attracted to. So the interplay of these two final states will also affect the nature of this 1405 state. In terms of theory, the chiral unitary theory combines chiral Lagrangians together with, and their low momentum interactions together with unitarity between different channels that have the same quantum numbers. So in this theory, there are so-called fundamental states, for example, the ground state pseudoscalar mesons, and also the octet of baryons. And these states can be sort of thought as being fundamental. So these fundamental mesons and baryons can interact with each other, and they can dynamically generate new resonances. So this is in contrast to some other models where you have poles in the complex energy plane which correspond to the resonances, and they just happen to be there at those masses and widths. This is a little different approach where you think that these fundamental particles are actually interacting to create these new resonances. So within this chiral-unitary approach, the lambda 1405 is sort of a textbook example of how new resonances can be created by these interactions. So one of the recent developments in this theory is that they are predicting that the lambda 1405 that we observed is actually made out of two poles in the complex energy plane. So that means that the theorists did a calculation, and if you look at this complex energy plane, then what they did was they started from complete flavor SU3 symmetry, and as they broke that flavor SU3 symmetry back into the real world, what they found was that the poles in the complex energy plane would evolve into two poles right next to each other. So the lambda 1405 that we're observing would actually be a superposition of these two poles. So this is what the chiral-unitary theory is telling us about this state. And furthermore, they're saying that these two poles would be excited differently in different experiments. So I'll talk a little bit more about this double pole theory later on with the results. The chiral-unitary theory also predicted what the line shape of the lambda 1405 would be in photocorrection. So this is the experiment that we did, photocorrection of the lambda 1405. And if they did this calculation based on the chiral-unitary amplitudes, and what they found was that the sigma pi channels would have this very sharp drop-off at the NK bar threshold because there's this strong coupling. But also the main prediction was that each of these sigma pi line shapes would be very different from each other. So if you produce this lambda 1405 state, you're going to have very different shapes depending on the decay mode that you're looking at. The reason for this is because there's the dominant isospin 0 amplitude, which of course corresponds to the lambda 1405, but there's also an isospin 1 amplitude that is there due to the dynamics of the interacting particles. So this isospin 1 term appears in the charge modes, and there's also interference with the isospin 0 term, and that makes these differences for the different charge modes. So this was the prediction from chiral unitary theory, and this was what we set out to either confirm or reject. So the second part of my talk will be about the class results. So class did this measurement, and we have published a string of papers regarding the lambda 1405. So I'll talk about what we have learned. So class took a very large data set called G11A about 10 years ago. This was a very large data set with over 20 billion two-track trigger events. And the goal for this analysis was to measure the line shape for all three sigma pi channels. So this is just a very simple cartoon of what the experiment was about. So we had a photon beam coming in at different energies. We interact with the proton target, and that produces three particles, the K plus and the sigma pi pair. So the sigma pi pair, of course, is what the lambda resonance is in. And since the class detector does not detect the sigma particle itself, but it detects its daughter particles, but because this decay is so far removed from the strong interaction, we can think that we are creating this strong final state of these three particles, K sigma pi. So let's jump directly into the results of our analysis. So we have done the most precise measurement of the lambda 1405, and furthermore, we have done a measurement of the three sigma pi channels simultaneously. So this is something that has never been done before, and we have extremely good statistics to show our line shapes. So we have results in 9 different bits of photon energy coming in, and if we plot the line shape of the lambda 1405, we're just plotting the sigma pi invariant mass spectrum. And what we see is that the spectrum is very, very different for each of the different sigma pi channels. So if we look at the sigma plus pi minus mode, which is in red, you can see that this is peaking at a mass about 1420 MeV and has a little bit narrower structure compared to the other channels. The sigma minus pi plus mode in green has a rather broad structure and seems to peak at a higher mass, lower mass about 1400. So you can see that qualitatively, the line shapes are very, very different from each other, and this seems to be, this is very exciting because this is something that has never been seen in another particle. Just for reference, this dashed line here is a Bragg-Wigner shape that is taken from, that is plotted using the PDG values for the mass and width of the lambda 1405. So you can see that the PDG values actually don't really correspond very well to what we actually see in the photocorrection experiment. So that was for low energies near the threshold of lambda 1405 production, and we can also look at the results at higher energies. So if you look at that result, then we see that the difference in the line shapes is not as prominent, but you can still see the prominent features. The sigma plus pi minus mode in red still peaks at the highest mass, about 1420, and the sigma minus pi plus mode still has a broader structure at the lower masses. So the differences are not as prominent, but we still do see some differences, and this is also interesting. So what does the chiral unitary theory tell us about our results? So after we published our results about the lambda 1405, the chiral unitary theorists came back to us and did a fit to our data results. So you can see here these results were published after our paper came out, and for the 9 different energy bins that we had, the chiral unitary theorists did a fit with their amplitudes with some adjustment of parameters, and they were actually able to fit our data very well. The interesting thing that came out of this was that there's this isospin 1 amplitude that interferes with the main isospin 0 amplitude to produce the difference in the line shapes. And if they extract that isospin 1 amplitude out, it turns out that there is going to be this cusp kind of behavior happening at the NK bar threshold for this isospin 1 amplitude. So this is a situation that is very similar to what happens to the A0 980. And they don't go as far as to claim that this is a resonance, but they do claim that there should be this cusp-like structure in isospin 1. So we're also probing what can happen in the isospin 1 channel in this mass region, and this also seems to be a very interesting development. Another group that uses the chiral unitary amplitudes also published a result. So this other group also did a fit to our data, so you can see that they were able to fit our data very well with their amplitudes. And in this case, they were only confident that this chiral unitary approach would work in the low mass region, so they restricted their fits to the low energy regions. The difference with the previous analysis was that they also took into account the differential cross-sections that we measured. I'll show those results in a little bit, but they also took those differential cross-section results into consideration also, and they tried to do some simultaneous fit to extract the parameters for the lambda 1405. So in this analysis, one of the main focuses was I talked about the double poles that could contribute to creating this lambda 1405. And in this case, they try to focus on which of the 2 poles was actually producing lambda 1405. So their analysis suggests that it is actually the higher pole that is thought to couple more strongly to the NK bar final state that is actually being excited in the photopression of this lambda 1405 state. So these people are planning a more extensive analysis of the full data set that class has published, and hopefully this will allow us to learn a little bit more about what is going on in this mass region. Now I move on to the cross-section results that we have published. So we measured the lambda 1405 line shape for the 3 different sigma pi channels, so we can also measure the differential cross-sections for those channels also. So each sigma pi channel was measured separately to see if there's any difference in the cross-sections, and we also measured the nearby sigma 01385 and lambda 1520. So this is exciting because we are measuring 3 different excited hyperons simultaneously within the same setup, and this is something that hasn't been done before, and also it's interesting because of the nature of the 3 different hyperons. So the lambda 1405 is thought to be this dynamically generated state that is very different from other resonances. The sigma 1385 is thought to be just one of the decouplet baryons that you show up. This is a partner with the deltas and the other particles in that decouplet. The lambda 1520 is usually thought to be a flavor SU3 singlet. So you can see that all of these states have very different quantum numbers and also thought to be very different resonances. And we're doing a measurement of all 3 at once. So here are the results for the lambda 1405 differential cross-section. So we had 9 different bins of energy, so I'm showing all these 9 bins at once. And these are all shown as a function of the kaon center mass angle. So to produce lambda 1405, you need to conserve strangeness, and to do that, you need to create a kaonic association. So we are plotting everything in that kaon angle in the center mass frame, and the differential cross-sections are shown like this. So what you notice is that in the lowest energy bin, the lowest energy bins, you have different behaviors for each of the different sigma pi modes. So the sigma minus pi plus mode shown in green here seems to have a rather steady rise as you go towards the 4 kaon angles. You can see that behavior right here. whereas the sigma plus pi minus mode seems to have a rise towards the forward angles, but then it sort of drops off as you go towards the more extreme forward angles. So qualitatively, there's clearly a very different behavior for all three sigma pi cross sections. So the differences that we see are also, of course, correlated with the region that we saw the difference in the line shapes. And as you go to the higher energy regions, what you see is that all three channels seem to be dominated by the forward cross section, and it seems like there's a steep rise for all three of them, and the agreement between the channels is much, much better. So we think that at the higher energies, there's some kind of kaon T-channel exchange mechanism that is producing this lambda 1405. We can also do a comparison of the three excited hyperons. So in this case, I have the same kind of panel for the sigma 1325, 1405, and lambda 1520. And you can see we have results for all three of these hyperons. So at the lower energies where the sigma 1325, 1405 have lower mass, that makes it easier to produce them. So those two states have a higher cross-section compared to lambda 1520. But you can see that at about these energies, the lambda 1520 cross-section seems to be higher than the other two hyperons, and this seems to be a trend that continues to the higher energies. So for the sigma 1325 and 1405, even though these two states seem to have very different characteristics or nature, if you look at the differential cross-sections and photoproduction, what you're seeing is that the black for the 1385 and blue for the 1405 actually follow each other quite well. So it seems like they have very similar behavior in terms of cross-section. We also extrapolated our differential cross-section results to all angles to try to determine the total cross-section for each of these hyperons. And we did a comparison with the ground state hyperons. So this is the total cross-section plotted against the incoming photon energy. So these are our results, the 9 energy bins that we have. So also plotted here are the cross-sections for the ground state K plus lambda and K plus sigma 0 channels. And what we see is that the excited hyperon cross-sections have a cross-section that is rather similar in size to the ground state direction. So the reason why this is interesting is because in recent years there has been a lot of activity involving these ground state hyperon channels, because some intermediate and star states can couple to them, and we can actually probe for intermediate and star states by looking at these channels. So because the excited hyperon states actually have a cross-section that is rather similar in size to these, then we can actually, if we actually had enough of a fine binning for these excited states, we could also probe for any kind of intermediate and star states coupling to these excited channels also. So this has actually been done already, and after we published our cross-section results, some theorists started to do some fits to our lambda 1520 data, and this has led to some suggestions of an star state. So currently the PDG lists a 2-star N-star 2080 state. This is now called the N2120 state in the newest PDG, but this is still a little bit controversial. You can see that this is only a 2-star state, but a fit to our lambda 1520 results suggests that with a regime plus resonance effective theory approach, this shows that there is an N-star 2120 state that is required to fit the data well. So 2 independent theorists came up with these models, and in both cases, the conclusion was to fit the data well, you would need this N-star 2120 state with spin parity 3.5 minus to get a good fit to the data. So the final part of my talk will be about the spin and parity of lambda 1405. So this was not part of the initial goals of this experiment, but this was something that I picked up during grad school, and this is sort of something that I am very happy that we were able to get this published. So as a grad student, I was learning about the lambda 1405, and I came across a review article for the PDG by Richard Gallitz. So Richard Gallitz studied this lambda 1405 state for a very long time, and this was one of his lifetime projects. So he wrote a PDG review in 1998, and in that review it says, the Weier's-Spencer test on these data, any spin in either parity. Neither J nor P has yet been determined directly. So that got me thinking, okay, so how do you measure the spin and parity of an excited hyperon state? And that led me into a new road on the analysis of the number 1405, and these are the results that I'll show you. So just to give you some historical perspective, almost all theories just assume the spin and parity of this number 1405 state. So this is based on the S-wave interaction of the decay particles of that state. This assumption is somewhat justified by the line shape of the 1405 because there's this drop in intensity at the MK bar threshold, and this will only happen if this state is coupling to those different channels in S-wave. But what we want is, we want to get direct experimental evidence or confirmation that this state is indeed a 1/2 minus state. So that is what we set out to do. So there's a method called the Byers-Fenster method, and this was a method that was developed in the 1960s. This is a very general method to determine the density matrix elements of any kind of resonance that you want to analyze. So what you do in this formalism is you form these multiple parameters called TLM. These are sort of like coefficients of spherical harmonics, and they characterize the density matrix elements of that particle. So the TLMs will determine the decay distributions and also the transfer of the polarization to its daughter particles, and you can calculate, you can have a complete description of the particle that you're producing. So I want to emphasize that there are no assumptions or model dependence from any kind of phenomenological QCD model, but this is just very, very, very basic quantum mechanics and just going through and grinding out a calculation based on these TLM parameters. So what we did was we did a calculation of the decay distribution and the polarization of the daughter particles parameterized with these TLMs in the Byers-Fenster basis, and we did a comparison with the data distributions to get a description of the 1405. So in the class analysis, what we did was we selected a high purity kinematic region. So if we looked at one specific energy and angle for the 1405 region, then this is just plotting the sigma pi invariant mass again. We use the sigma plus pi minus channel. And you can see here that we have this region that's very clean. We have the 1405 shown with this red shaded area. And there's a little bit of contamination due to the sigma 1385 and also a little bit of K-star background. But basically we have a very clean sample of 1405 events. So one thing that we exploited in this experiment was that if we have an unpolarized beam and target, then the polarization of lambda 1405 can only be out of the production plane. So if you think of this production plane here in the center mass frame, you have the proton-proton interaction, and out come the K plus lambda 1405. So the 1405 polarization can only be out of the production plane. So that polarization corresponds to some of the TLM parameters in this Byers-Fenster method. And what we did was we determined the spin and parity of the 1405 as follows. So if we measure the decay distribution to sigma pi, then the complexity of that decay distribution allows us to determine what the maximum spin of that particle is. That determines the spin J. And then if we do a measurement of the polarization of the daughter sigma plus with respect to the sigma pi decay angle, then that gives us an idea of what the parity of that parent state is. So here in these cartoons, what I'm showing you is the polarization transfer for two different scenarios. So if the 1405 is 1/2 minus, as everybody expects it is, then you have the lambda 1405 polarization that is going to be out of the production plane. So that's shown by this red arrow here. So in the case of a 1/2 minus decay, which is going to be S-wave decay to sigma pi, what's going to happen is that the sigma plus polarization is going to be constant, independent of the angle that it decays from this lambda 1405. So you can see that the polarization of the sigma plus, which is shown by these blue arrows, is going to be always constant. In the case of a 1/2 plus resonance, what's going to happen is you have this 1405 state that is produced polarized, and the polarization of the sigma plus is going to do a complete rotation depending on the decay angle from this 1405 decay. So you can see that the polarization, if it's going to be in this direction here, then it has to be in the opposite direction if it's going out at 90 degrees and going to come back at 180 degrees. So this is the way that we're going to determine the spin and parity of this 1405 state. So in our class analysis, we looked at the decay distribution of the sigma pi system from the 1405, and what we saw was that we were able to match the decay distribution to sigma pi without any kind of adjustment of these parameters. So the parameters would be the TLMs and the Byers-Spencer method, and if we did need to have significant adjustments, then that would mean that the state is not spin 1/2, but is a higher spin. But we didn't have to do that, so the conclusion here is that the 1405 does have a very isotropic decay distribution, and this is the best proof possible that it is indeed a spin 1/2 state. So given that the state is spin 1/2, we can also look at the polarization of the sigma plus as a function of the decay angle. And what we saw is that if we made the data into 5 bins in different regions of this angle, we saw that the polarization is very, very constant. So this red line here corresponds to the hypothesis that the 1405 is a spin 1/2 minus state, spin parity 1/2 minus state, and the dashed blue line here corresponds to the hypothesis of 1/2 plus. So you can see very clearly that we can completely rule out the 1/2 plus hypothesis, and we have determined for the first time experimentally that the 1405 has indeed spin parity 1/2 minus. So what does this result tell us? This result here was a rather vanilla result because nobody expected the 1405 spin parity to be anything other than 1/2 minus. So that part is fine. But since the formalism that we used is completely general, we can actually use this formalism to determine the spin imparity of any other state that we are interested in. So one example would be the spin imparity of an excited cascade state. So in the decay of an excited cascade state, you can have decays, for example, like lambda k, and these would have the exact same formalism as the 1405 decaying into sigma pi. So these cartoons here, what I'm showing is our class, this is our current class analysis, where you have the number 1405 produced. This decays into sigma pi, and by measuring the polarization of the sigma plus, we determine the spin imparity of the 1405. Oops, sorry. In the 12GeV era, if we have excited cascade states produced by class 12 or BlueX, then this excited cascade state decaying to lambda k minus would have the exact same formalism, and this would allow us to determine the spin imparity of this excited cascade state. So this is one of the exciting prospects for 12GeV physics to come in future years. And then finally, in the final part of my talk, I'd like to talk about some prospects, what we're learning from other labs that are looking into the 1405, and also I'll talk about some of the conclusions. All right, so after class published the photoprojection results, we also published results from electroprojection. In this case, there was an experiment from a long time ago that used electroprojection data, and there was a paper that looked into the sigma pi spectrum. So this is the correct acceptance corrected result for the lambda 1405 region, and you clearly see this two-hump structure of the 1405. So again, we get back to this two-pole theory that came from chiral-unitary theory, and in this paper there was a fit done with Breit-Wigner functions, and this extracted the mass and width of these two hump shapes. So the interesting result was that the strength of the pole at the higher mass actually increases with the increasing Q-square, the photon virtuality, and this was something that was not predicted, and there's no theory that actually talks about this yet, but this seems to be some new development for the 1405. The hottest collaboration at GSI did an experiment using proton-proton collisions, in this case producing the cable standard 1405 system with an additional proton. So they presented results of their sigma pi spectrum, and the interesting thing here is that the peak of the 1405 actually shows up at a lower mass than 1400. So the dashed line here corresponds to a mass of 1400, and in both of these sigma pi channels, the hottest collaboration reported that they saw a peak lower than that at about 1385 MeV. So this is in contrast to our sigma plus pi minus results, where we actually had a peak at about 1420. So there's clearly some difference between the different production mechanisms. So just to talk a little bit about that, in proton-proton reactions, you have a total isospin of 1. So therefore, you can think that there's not a severe isospin interference between isospin 0 and isospin 1 channels. So that may be the reason that they see this very different line shape in this proton-proton experiment. For future planned experiments, the BGOOD experiment at Bonn is planning to do a photoprojection experiment up to 1405 using the BGO that they have, and also a forward spectrometer. So data taking, I hear, is going to begin soon, and there's a proposal to measure the line shape and the cross sections of the lambda 1405. So in conclusion, class has published new results showing that the lambda 1405 does indeed have strong dynamical effects that have not been seen in other particles. Photoprojection is only part of the story, and to get a more complete picture of what the lambda 1405 is and what the particle interactions are at these energies, we will have to have more experiments at other labs to find this out. So class 12 and GLUX may produce further electrophotoprojection results at higher energies, and this may also contribute to our understanding of the 1405 and also other excited hadron states. So investigations into what I call the strangeness frontier will continue into the JLab 12GB era, and hopefully we'll have some more results in the strangeness -1 channel for the lambda and sigma states, and also for the cascade states if possible. So at the end, I would just like to give thanks to all of the people in the class collaboration for helping me out over the years, all of the review committee members, and also my thesis advisor, Reinhard Schumacher at CMU, and my current advisor, Matt Shepard at IU, for allowing me to work on these things deep into my postdoc. Thank you.
Thank you, Kay, for your hard work on the lambda 1405. Do we have any comments or questions for Kay? Oh, Volker?
Okay, I was interested in seeing would be seeing the comparison between the PP signal and the electroproduction. Is it possible that in electroproduction this lower peak is about where you see the peak at PP? And the second peak is not seen in the PP interaction?
Yeah, so I guess the peak here would be about 1370 or so. So it's a little bit off compared to the PP result, where they claim that a Monte Carlo simulation at 1385 MeV, but peak seems to fit the data best.
Okay. But close.
Any other comments, questions? Okay. Well, let us thank Kay again for his very hard work. And our last talk of this users meeting will be by Victor Mokeev, and he will show us some stuff from class. So, last talk.
I am going to present the current status in the studies of excited nucleon states, spectrum and structure, from exclusive pi and electroproduction of protons measured with the class detector at Jefferson lab. The studies of excited nucleon state, spectrum and structure represent important and absolutely needed part of effort in order to explore dynamic of strong interaction in the regime of large core-gluon-Raman coupling, so-called non-perturbative regime. The studies of N-star spectrum and structure offer unique information on how non-perturbative strong interaction generates excited nucleon states of different quantum number. As we well know, the ground and excited nucleon state consist of infinite amount of elementary QCD quark and gluons, which are continuously created and annihilated. In order to deal with such complexity, it is customary to employ in a relativistic covariant way the effective field theory object, dressed quarks and dressed gluons, Ground and excited nucleon states is the bound system of free dressed quark bound by complex non-perturbative strong interaction, shown in this cartoon by this plot. Dressed quark generated from paired QCD quark in dressing processes by gluons and Q-bar pair coupled to gluon fields in regime when quark-gluon Radian coupling becomes large. In this way, we generate effective dynamical object with mass, structure, and other properties dependent from distance scale or momentum running over quark propagator. Two conceptually different approaches developed for description of dressed quark running mass, Dyson-Schwinger equation of QCD and the lattice QCD, both predict pronounced dependence of dressed quark mass function as a function of momentum running over quark propagator. At momentum less than 2 GeV, we have substantial increase of dressed quark running mass from small value, which correspond to almost undressed perturbative QCD quark, to the value above 300 MeV, which correspond to fully dressed quark employed in constituent quark model. This mass generation from nothing through chiral symmetry breaking processes depicted here is responsible for generation of more than 98% of dressed quark mass and consequently hadron mass. Higgs mechanism, which is responsible for generation of less than 2% of hadron mass, is almost irrelevant in the real world of meson and baryon. And that's why this our experiment here at Jefferson Lab will address the challenging question on the nature of more than 98% of hadron mass in universe. Furthermore, this momentum dependence of the dressed quark mass function reflect transition between almost perturbative QCD regime here to strong confinement regime at small momentum running over single quark less than 0.5 GeV. The studies of elastic form factor and transition end-to-end star electrocoupling will allow us to map out the dressed quark mass function. In this plot, I show the result of Dyson-Schwinger equation on evaluation of ratio of elastic form factor G over Gm carried out starting from QCD Lagrangian for different momentum dependence of dressed quark mass function. As you may see, different momentum dependence of dressed quark mass function result in very different evolution of this ratio with Q square, in particular at high Q square. Therefore, as soon as in 12 GeV era we will be able to measure this ratio in a wide area of Q square, we will obtain first exploratory information on dressed quark mass function. For reliable access to dressed quark mass function, we need to study combined elastic form factor and transition end-to-end star electrocoupling. Dressed quark mass function should be the same for dressed quark in the ground and in excited nucleon states. Therefore, consistent results on dressed quark mass function obtained in independent analysis of elastic form factor and transition end-to-end star electrocoupling offer an evidence for reliable extraction of this fundamental quantity. Making dressed quark mass function addressed most challenging and still open question of the standard model. How dominant part of hadron mass is generated non-perturbatively, and how confinement in baryon comes from QCD. That's why the study of excited nucleon state of spectrum and structure represent one of the central directions in contemporary hadron physics. And star electroexcitation can be fully described by free and star electrocoupling listed over here. They are proportional to the helicity amplitude for the transition between the initial photon-proton state and final and star delta star states for different helicities of the initial photon and proton. In order to determine their electrocoupling and their Q square evolution from experimental data, we are studying different exclusive meson electroproduction channel schematically depicted in this cartoon. Full amplitude of any exclusive meson electroproduction channel represents superposition of star excitation in S channel and complex set of non-resonant mechanisms. Therefore, in order to access star electrocoupling and their hadronic parameters, first we need to separate resonant and non-resonant contribution. So far, it can be done only within the framework of phenomenological reaction models, which should be rigorously tested against experimental data. However, even in this case question arises, how reliable this separation is, and how reliable and star electrocoupling being determined within the framework of phenomenological reaction models. Fortunately, the studies of different exclusive meson electroproduction channels make it possible to answer this question. Non-resonant mechanism in different meson exclusive electroproduction channel completely different, and star electrocoupling should remain the same because this vortex is independent from this vortex, and this is model independent state. Therefore, consistent result on star electrocoupling obtained in independent analysis of major and different exclusive meson electroproduction channel offer a sound evidence for reliable extraction of these fundamental quantities. Class detector provides the dominant part of available worldwide information on most exclusive meson electroproduction channel which are relevant in star excitation region. In this plot, I show yields of different exclusive meson electroproduction channels measured with the class detector. Single and charge double pi exclusive channel are two major contributors in star excitation region. They both sensitive to n-star state, and they provide complementary information on spectrum and structure of excited n-star states. As you may see, n-star state with masses less than 1.6 GeV decay both to single pi and double pi final state, but preferentially to single pi final state, making the study of single pi processes the major source of information on electrocoupling of low-light nuclear excitation. However, this information extracted in analysis of single pi electroproduction can be independently checked in the studies of charge double pi electroproduction, since many of low-lying nucleon excitation also have substantial hadronic decay to double pi final state. Instead, most of high-lying hadronic final state decay preferentially with 2 pi emission, making charge double pi electroproduction channel most effective tool for extraction of high-lying n-star electrocouplings. Several phenomenological approaches have been developed for extraction of nucleon resonance electrocoupling from independent analysis of single and charge double pi electroproduction. Analysis of single pi electroproduction data was carried out within a framework of two conceptually different approaches: unitary isobar model, which represents minimal set of gauge invariant three-level diagram, and unitary dispersion relation technique. Both approaches provided good description of all available worldwide data at W less than 1.8 GeV and at Q square up to 5 GeV square. Example of data description is shown in this plot. In the left panel, I show a description of W dependencies of pi plus neutron electroproduction data measured at different center of mass pi plus emission angle. On the right panel, I show a description of multiple from different exclusive structure function for pi plus neutron electroproduction. Both approaches provided equally good description of experimental data, and difference in the star parameter extracted within the framework of these two approaches offer an estimate for systematical uncertainties of star parameters related to use of model assumption. Class detector for the first time provided information on 9 independent charge double pi single differential cross section at W less than 2.3 GeV and at Q square from 0.2 to 1.5 GeV square. Wealth of this experimental data make it possible to establish all essential contributing mechanisms to this exclusive channel, from their manifestation in observables as peaks in invariant mass distribution, sharp dependencies in angular distribution. Within the framework of the strategy, phenomenological approach GM has been developed with the primary objective of extracting nuclear resonance electrocouplings and their pi delta entroproton hadronic decays from combined analysis of all available observables on charge double pi electroproduction. This approach provided good description of experimental data at W less than 1.8 GeV and at Q square up to 1.5 GeV square. Example of data description shown in the left panel together with cross-section for different contributing mechanisms. In the right panel of this plot, I show separation between resonant and non-resonant contribution achieved from the class data feed within a framework of GN model. As you may see, shape of resonant and non-resonant cross-section are very different in all observables, allowing us to access resonant contribution and to obtain and start electrocoupling. In this plot, I show electrocoupling of Roper resonance and 1520 3/2- state determined from independent analysis of single and charge double prime electroproduction. The results obtained from this independent analysis are consistent. Actually, they coincide with error bar. Consistent results on electrocoupling of low-lying nucleon excitations obtained from two major exclusive meson electroproduction channels with completely different non-resonant contribution and within a framework of different reaction model strongly suggest capability of reaction model developed by class collaboration for reliable extraction of resonant parameter from independent analysis of single and charge double prime exclusive electroproduction channels. Physics analysis of the class data on instar electrocoupling revealed that the structure of excited nuclear states at Q square up to 5 GeV square represent combined contribution from external meson baryon cloud and internal core of free rest core. In this plot, I show evaluation within the framework of Dyson-Schwinger approach for backward core contribution to transition and to delta magnetic form factor in comparison with available experimental data. As you may see, evaluated value of form factor are much smaller, in particular at Q square less than 1 GeV, showing presence of additional contribution on top of quark degrees of freedom, which were taken into account within the framework of Dyson-Schwinger approach. This additional contribution comes from so-called meson baryon dressing, when the initial photon and proton create all possible intermediate meson baryon state, all possible intermediate meson baryon state through sequence of all possible meson baryon rescattering, eventually create n-star state. Argona-Saka collaboration extracted from experimental data on single pair photo, hadron, and electroproduction the amplitude of this process. And if we subtract from this electrocoupling this amplitude, we obtain infrared from experimental data backward core contribution shown here by red dashed white. This red dashed white actually much closer than experimental data on rest electrocoupling to Dyson-Schwinger equation evaluation. And Dyson-Schwinger equation evaluation becomes consistent with experimental data on backward core contribution if we take into account the contribution from anomalous chroma and electromagnetic moment of the rest core. At this point, we concluded that the structure of excited nucleon state measured in experiment represents combined contribution of backward core and external meson baryon cloud. Dyson-Schwinger equation of QCD provided a reasonable description of backward core contribution, and measuring transition form factor, we are able to access rest core mass function with help of Dyson-Schwinger equation approach. However, first we need to isolate the contribution of backward core from experimental data within a framework of coupled channel approach. The studies of n-star electrocoupling over spectrum of excited nucleon state reveal complex interplay between quark and meson baryon degrees of freedom in excited nucleon state structure. For delta resonance, meson baryon degrees of freedom becomes relevant up to Q square 5 GeV squared. Instead, for the state T1 3 15 20 3/2 minus, the contribution from meson baryon cloud becomes negligible at Q square above 2 GeV squared. In this kinematical area, we already have class data on electrocoupling of the state, and it offers promising opportunity from electrocoupling of the state directly access backward core. And this kinematical area is preferential for the studies of the rest core mass function, since there is no need to subtract model-dependent meson baryon dressing. What we need from theory is Dyson-Schwinger or any other QCD-based model evaluation of backward core contribution to the structure of this excited state. Now the question arises, would it be possible to access from experimental data meson baryon cloud? Recent studies of electrocoupling of 1675 5/2 minus state provided positive answer to this question. Murhau's selection rule predicts zero electrocoupling of this state, excited of proton time. More elaborated work model, which takes into account configuration mixing, predicts small value of star electrocoupling. Electrocoupling obtained in experimental data much larger and consistent with absolute value of mass and baryon cloud inferred from experimental data by Argon-Osaka collaboration. Therefore, electrocoupling of this state open access from experimental data to mass and baryon cloud for 1675 half minus state excited of proton time. Therefore, structure of excited nucleon state at small q square is very complex. It determined by combined contribution of mass and baryon and 4 degrees of freedom. And currently, only approach I know which is capable have potential to describe all this complexity starting from QCD Lagrangian is lattice QCD. Lattice QCD is making promising progress in order to develop tools which allow us to compare our result of star electrocoupling with expectation from QCD Lagrangian. These tools, however, are very complex. It is not straightforward comparison. And I strongly recommend excellent talk by John Dudek addressed to this issue if you really want to understand real capability of lattice QCD to help us in physics analysis of N-star spectrum and structure. W dependence of fully integrated charge double pi and electroproduction cross-section show pronounced peaks at W 1.7 GeV. For the first time, this structure was observed in the class data published in 2003, and that time we found two equal interpretations for description of experimental data in W square mean inside the structure. We can consider the contribution from conventional N-star state only, but in order to describe experimental data on 4 differential cross-sections in this structure, we have to modify substantially hadronic decay parameter to pi delta and proton final state for conventional 3½ plus 1720 resonance in comparison with available previously from experiment with hadronic proton. Previous data indicate dominant decay to proton final state. However, for description of class data, we need to have dominant decay to pi delta final state. Alternatively, we may keep pi delta and proton hadronic decay of all conventional state, instant the range of the APTG uncertainties, but in this case, in order to describe this data, we have to implement new candidate state with electrocoupling, quantum number, and hadronic parameters derived from the data feed. That time, we were unable to see any preference between these two hypotheses. However, that time, we were analyzing only 5 one-fold differential cross-section, and now we are capable to analyze 9 one-fold differential cross-section. Furthermore, our reaction model was upgraded considerably. Therefore, now we refeed class data on 9 one-fold differential cross-section in the recent version of our reaction model in the kinematic area shown here. The studies were carried out under two assumptions. First, we consider the contribution from conventional state only. However, we varied pi delta and proton hadronic decay width for all conventional state contributing to the structure at 1.7 GeV in a wide range and feed them to the data. Secondly, we feed this data again, assuming the contribution from this candidate state on the top of conventional state. We found preferential data description implementing new baryon state. Implementation of new baryon state allow us to better describe the data on angular distribution over rotational angle of the final pi minus proton pair with respect to the free momentum of the pi plus. Let's call it alpha rotational angle. Then we further investigate the reason for observed improvement. We found that in order to describe pi minus, pi plus, and proton angular distribution, we need to have the contribution from resonance state with spin parity 3½ plus. If we have just one resonance, with imperative Lee-Howe class, as in the case of conventional state code. This single state should have major decay to pi delta final state in order to reproduce delta peak in pi plus proton invariant mass distribution, and small minor proton decay, less than 15%, in order to be consistent with pi mass distribution, where we cannot see any peak. However, such hadronic decay pattern does not allow us to describe data on angular distribution over alpha rotational angle. We failed systematically to describe this angular distribution in several beams of W and Q square inside the structure at 1.7 GeV. We found that in order to describe this angular distribution, we need to have a resonance state with spin parity 3½ plus with completely other hadronic decay pattern. Hadronic decay to the pi delta and rho proton final state should be comparable, and branching fraction to rho proton final state should be above 30%. So, in order to describe this angular distribution, we need to have 3½ plus state with branching fraction for rho proton decay more than 30%. From the other hand, in order to describe pi mass distribution, we need to have 3½ plus resonance state with rho proton decay below 15%. This contradictory requirement just means that there is no way to describe all 9 one-fold differential cross-section implementing just conventional state, whatever hadronic decay pattern we assume. We need to have two 3½ plus imperative state. One of the state we call new baryon state should have major decay to pi delta final state and minor to rho proton final state to describe angular distribution pi plus pi minus proton and invariant mass distribution. Instead, second state we call conventional state should have comparable decay to pi delta and rho proton final state in order to describe this angular distribution, and we avoid formation of rho peak here, keeping small enough electrocoupling of this state. We have systematical improvement in description of alpha angular distribution implementing new baryon state. Electrocoupling of new baryon state extracted from class data are shown here. Right now, it is only candidate state for which we have information on Q-square evolution of N-star electrocoupling. For all other candidate states, we just have information on photocoupling, no information on Q-square evolution of N-star electrocoupling. Hadronic decays are shown in this table. This new state manifests consistently in all Q-square beams with the same hadronic decay parameter. All these facts support existence of new baryon state. Problem with new baryon state is that implementation of new baryon state gives us very modest improvement in description of experimental data. Actually, we improve description of just one of 9 one-fold differential cross-section. Therefore, future analysis of the class data on charge double pi photoproduction and electroproduction in a wider Q-square area, complemented by the data of KY exclusive channel, would be very important in order to understand the nature of the structure at 1.7 GeV. For the first time, charge double pi in electroproduction channel provided preliminary information on electrocoupling several high-lying nucleon excitation listed over here. All this excited nucleon state shown in this plot decay preferentially with 2 pi emission, and double pi exclusive channel is only source of information on electrocoupling of the state. Electrocoupling of the state obtained in independent analysis of several W intervals are consistent, as you may see in this plot, showing reliable extraction of these parameters. Database for charge double pi in electroproduction channel keep extending. We have almost completed and ready for internal class collaboration review charge double pi and photoproduction data. In each bin of W, in W interval from 1.66 GeV to 2.5 GeV, we have 9 one-fold differential cross-section, and on top of that, 28 two-dimensional correlated differential cross-section. We also extending database on charge double pi in electroproduction, extending Q-square coverage. In near-term future, we will have charge double pi in electroproduction data and Q-square area from 0.4 to 5 GV squared, fully integrated Church double pi vector production cross-section available in this data are shown in this plot. As you may see, as Q square increases, relative contribution of resonance structure also increases. Therefore, high Q square regime is preferential for the study of high-line nucleon excitation. However, data of better accuracy and more observable available in the floating point. Therefore, combined future analysis of all this data will provide us information on Q square evolution of electrocoupling of most excited nucleon state at mass range up to 2 GeV, and I believe provide final knowledge on the nature of the structure at 1.7 GeV. In conclusion, high quality class electroproduction data for the first time provided information on electrocoupling of most excited nucleon states in mass range up to 1.8 GeV. Analysis of the class data on Church double pi electroproduction reveal preferential way to describe this experimental data, implementing new baryon state with quantum number derived from the class data feed. Electrocoupling and hadronic decay parameters of the state were determined from the class data feed. Physics analysis of the class result on N-star electrocoupling reveal complex interplay between Meson baryon and quark degrees of freedom in N-star structure. The studies of excited nucleon state of different quantum number is essential in order to disentangle between this contribution to nucleon resonance structure. Available class data offer excellent opportunity for theory to explore manifestation of non-perturbative strong interaction, information of excited nucleon state of different quantum number, and information on structure and electrocoupling of excited nucleon state will be extended in near-term future, I was saying previously. After 12 GeV upgrade, class 12 will be only facility for a SIM worldwide, which will be capable to obtain information on electrocoupling of most excited nucleon state at Q square from 5 to 12 GeV square, largest Q square ever explored in exclusive regime. And it provides access to interaction of the rest quark, which is responsible for N-star formation of different quantum number, and address fundamental question of the standard model. How dominant part of the hadron mass comes from QCD, and how confinement in baryon sector comes from QCD. Therefore, more new exciting results will come soon from the studies of excited nucleon states. Please stay tuned and thank you.
Victor, any questions for Victor today? No questions for Victor? Oh, wait.
You emphasize how at larger Q squared you're expecting that the resonance signals will be more readily identified. Why do you think that?
Okay. This is just expectation. It is not firm statement. Let's consider W dependence of Church double pi electroproduction cross section at Q square from 2.2 to 4.6 GeV squared. As you may see, a resonance structure at maximal Q squared becomes more pronounced. Furthermore, from the studies of smaller Q squared below the 1.5 GeV squared, I know reason why relative contribution of resonance signal becomes larger. Because non-resonant contribution fall down according to monopole fit roughly. Instead, resonance signal has much smoother behavior with Q squared because of A1/2 component contribution.
I was expecting you to say something about meson clouds.
Meson cloud. Meson cloud, actually what we learned from meson cloud. Meson cloud relevant for all N-star states we analyzed so far. Meson cloud contribution decreases with Q square, which correspond to very simple picture of photon interaction with N-star, when photon high virtuality penetrate external Meson baryon cloud and interact with internal quark core. And based on this data, we expect that at Q square above 5 GeV square, major contribution should be from the quark core.
That's why this kinematical area is of particular interest. For the first time, we may access directly 4 degrees of freedom in star structure without any severe modeling of mass invariant degrees of freedom, which rely on many data which are incomplete, contradictory, and so on.
Very good.
Any other questions? Well, let us thank Victor again and all the speakers from this session. Very excellent session.
All right, I just want to thank everyone again for attending. It was a very interesting workshop. I hope everyone else did. Just a quick reminder, if you want to, we have the ballots and envelopes if you want to nominate someone for the DNP Executive Committee, and if you're looking for suggestions, the User Group Board thought Rolf Venn would make an excellent candidate for member at large. So please, if you want, you can fill those out here. Be sure to sign both the form and the envelope, and you can just leave them here. More importantly, we now have our first beam at well above 6 Jeff party over in F115. So 113, yes, thank you. So enjoy.